Now, what is probability? Probability is logically, scientifically, right? Logically, scientifically predicting the possibility of something happening. Right? Logically, scientifically predicting the possibility of something happening is called probability. Probability. So why do we learn probability? Why do we like probability? Because then we are in a better position to predict. When we can predict better, we can plan out things, manage things. Okay. So that is why we are interested in probability. So do we have only one way of predicting? Can you tell me different ways people use to predict things? Because probability is one way of predicting, right? For example, I will say when I throw a dice, possibility of getting 6 is 1/6. That is through my probability knowledge, logical, scientific way of predicting. I'll say 1/6. Do we have any other ways of predicting things? Because one way is probability. Of course, there are. Some people use different ways, right? So some people use their horoscope to predict what is going to happen in the near future, what vivahaya kariyanaada. Right? Some people go and saatarahano predict how they make horakam karanne. So those are our predictions. Right? Those are our predictions. And this is one type of prediction, probability. But this approach is 100% logical, scientific. Okay? Right, so that is what probability is. And probability and statistics are highly related topics. Unfortunately, in your syllabus, statistic is not there. That is very unfortunate thing to happen. Right? Unfortunately, in your syllabus, you have only probability because statistic is in the final year maths, which is optional. And a lot of students, they don't do that maths. That is another unfortunate event. Okay. So therefore, they should have added statistics into your semester one maths, but unfortunately, we are going to learn half of the stuff. That is only the probability. Okay. Because when we combine probability and statistic, the real power comes. Right. AI, data science, right? In general, science, engineering, business, economics, we heavily use, right? Heavily use. But anyway, just learn the probability half. Maybe you can do self-learning the statistic part if you are really serious about these areas. Okay, these areas. But probability, we go into a real depth, right? Really the depth. Okay. It doesn't mean that we are going to do a lot of new things. No, we are going to do mostly the things that you did in O level, but we are going to do it in a very purposeful, thoughtful manner. Okay, serious level. Right. So as I told you, everywhere there are usages of probability, right? Engineering, science, AI, finance, and everywhere. Okay, predicting things, even predicting the weather, predicting economics, trends. Right. So this is what we are going to do today. We are going to look at the basic terminology, the words that we use, and we are going to look at the basics of probability, the fundamental theorem of probability, and so on. Then some properties of probability, and then we look at what is meant by mutually exclusive events and what are the probabilistic rules related to that. Then we will look at what are independent events and what are the probabilistic rules, formulas where we can use to calculate probability of independent events. Then we will look at what is meant by conditional probability. And finally, we will look at Bayes theorem. Okay, that is your syllabus. Right. So the prerequisites. So you must be really, really good at your logic and sets. I told you sets and logic subject is related to so many areas, relational databases, probability, right? And also permutation and combination knowledge. That is why we did it before probability, right? How many possibilities are there? How many possible ways we can pick? How many possible ways we can arrange? So that we are not going to use those rules, but that gut feeling is going to really help uh, solving probability questions, because just knowing the rule formula is not going to work in probability. You need to use your own common sense, logical thinking, critical thinking. Okay. Right. So you must have that idea, what is a set, what is universal set, what is empty set, what is intersection, union, and complement, what is subsets, right? So you must have that idea. I hope you guys having those ideas, because anyway, we did it in this semester itself, okay? Right. So I already mentioned what is probability. Probability is scientific or logical, realistic way of predicting possibility of an event happening. But if I toss this coin, what is the probability of getting head? If I take a ball from this bag, what is the probability of getting red ball? So we can start like that, and then we can end up something like, if I do this investment, what is the probability of getting 10% profit? Okay. If you select this government, what is the probability of getting better? What is the probability of getting worse? So those are the things that the people must decide, calculate before go and vote in the elections. So party A, what is the probability of taking this country forward? Party B, what is the probability? Party C, what is the probability? So then they should go and vote. Okay? Or maybe they should say, what is the probability of me getting benefits if X wins, if Y wins, if Z wins? At least like that. අඩු කර තමන්ටවත් ප්‍රයෝජනයක් තියෙන්න බෑ. Right. So we'll look at the basic words first. What is mean by experiment, trial, outcome, sample space, and event. Okay. Sample space and event. Right. So what is mean by experiment and what is mean by trial of an experiment? Because these two words are heavily related. So experiment is doing an act. Simple as that. Doing an act which has possible outcomes. It's an experiment. Right? So as simple as throwing a dice. So when you throw a dice, it's an experiment because it has set of possible outcomes: getting one, getting two, getting three, getting four, getting five, getting six. It's experiment, right? Investing your money on particular shares, experiment, because it has possible outcomes. You get high profit, very low profit, no profit, even losing your money. It's experiment because there are so many outcomes. Even electing a government is experiment. So there are so many outcomes, right? So it can be a simple experiment like throwing a dice to a very complicated experiment like electing a government. Decide or making. So if you decide to marry, so that is also a sort of experiment, right? So many outcomes. It's experiment because there's nothing called this is the outcome. So then what is mean by trial? So trial is an instance of experiment. So if you throw it once, the dice, it's a one trial. If you throw it again, that is another trial, right? If you elect a government, it's one trial. If you elect another government in another 6 years, that is another trial. So experiment is selecting a government. Okay. Experiment, trials of the experiments. Okay. So your experiment can be a simple thing or compound thing. For example, your experiment can be throwing a dice. And at the same time, your experiment can be throwing a dice and tossing a coin. Do both. That is also experiment, but it's a compound experiment. And you can have trials of that. So therefore, experiment can be a atomic activity or compound activity. Right? Maybe you throw a dice is experiment. Throwing three dices, that is also experiment. You throw three dices. Then each dice has individual outcome and you have the overall outcome. Maybe the overall outcome is 5 to 6. So you need to stay with these basics and right very seriously because sometimes students are so fast that they don't spend enough time understanding the basics and they stuck in the theory parts. Right. So therefore, now we discuss about experiment, trial of an experiment, and every experiment or every trial of an experiment has one or more outcomes. For example, if you toss a coin, there are only two outcomes, getting head, getting tail. Forget about that uh, very rare situations, right? If you throw a dice, there are only six outcomes, getting 1, 2, 3, 4, 5, 6. Forget about those abnormal situations, okay? Those are rare situations. That is called outcome. Experiment, trial, outcome. Okay. So now we are going to look at what is meant by sample space. නියජ අවකාශය කියලා කියනවා. So now you must have very precise answer for what is sample space. Sample space is when you do experiment or trial of an experiment, all possible outcomes, if you take it as a set, that is called sample space. If you write down all possible outcomes as a set, it's called sample space. Okay. Does all the instance of experiment are trials? Yes. All the instance of experiment is a trial. If you have 10 instance of the experiment, 10 trials. Right. So sample space is set of all possible outcomes. You need to write down all possible outcomes. Okay. So it's very important, this word all. All. For example, if you throw a dice, the sample space is 1, 2, 3, 4, 5, 6. If you toss a coin, sample space is getting head, getting tail. That is where you need to understand the permutation and combinations also. Because you need to identify all possible outcomes. How many of those are there? Sometimes there can be infinite number of outcomes. Infinite number of outcomes for experiment. Right. So do this exercise. A dice with each side having 1 to 6 is thrown and a coin with head and tail is tossed simultaneously at the same time. Write down the sample space for the experiment. Right. You need to take a piece of paper and write down the sample space. Sample space must have each and every outcome of this experiment. And it must be a set. It's a compound experiment. Now you should have that terminology, right? It's a compound experiment. So if you do a trial instance of this experiment, what is the sample space? Or you need to write down all the possible outcomes. And it must be a set. And also tell me how many possible outcomes are there? What is the number of elements in the sample space? Just common sense, okay? So you can get one head, one tail, two head, two tail, three head, three tail, and so on. So you get 12 possible outcomes. So therefore your sample space consists of 12 possibilities. 12 possibilities. This is the sample space. 12 elements, 6 into 2. Now, is it a combination question or permutation question? Anyone? If you look at it as a combination or permutation question, is it a combination question or permutation question? Now, sometimes you may feel like, yes, I have understood, but sometimes still you have not understood. Yes, it's a combination question. So here we have two possibilities. Here we have six possibilities. So here we get, actually here we don't pick it. We get one out of two. Here we get one out of six. So usually we pick, but here we get because we don't have the control of picking. But we can think of it like picking also. Maybe the nature pick it, not you. Right. Do this exercise too. A coin is tossed repeatedly until getting heads. Write down the sample space for the experiment. So it's an interesting experiment. You keep tossing the coin until you get head. Write down the sample space. When you get head, you stop. One possibility is, let's call the sample spaces. You get head, then you stop. So the second possibility, first you get tail, then you get head. Another possibility, first you get tail, next time also you get tail, and then you get head. Tail, 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 head. So theoretically, there are infinite number of elements. Of course, we know that practically, most of the time, maybe by fifth experiment, sixth experiment, you have got the head and you have stopped. But theoretically, infinite number of possibilities are there. Because in theory, you can keep getting tails forever. Theoretically, right? I am not asking about practicality. So therefore, these are all possible elements. So therefore, you can't say exactly how many, right? Again, if you want exactly how many, we need to go into again probability. Say 80% of the confidence, this is the sample space. Anyway, let's not discuss that. Okay. Right. So now we move on to another concept, event. Now, a lot of students misunderstand what is mean by event. Now, what are the words we have used so far? Terms. experiment, trial, outcome, sample space. So this is an event. So a lot of students think that experiment and event is the same, or experiment and trial is the same. No, no. Event is completely different thing. Of course, these are all interrelated, but event is not experiment, event is not trial. Okay. So what is mean by an event? So event is imaginary thing. Event is in your mind. Event is your expectation. Right? So it's super important to understand this. So when you do an experiment or trial of an experiment, if you wish something, right? If you wish something, or if you imagine something that is related to the experiment, right? Related to experiment, right? Nothing else. So that is an event. For example, assume that you throw a dice with 1, 2, 3, 4, 5, 6. So how many events are there? How many things you can imagine about that experiment? So the simple answer is infinite number of events are there. Because you can imagine that let one getting one, that is an event. Getting two, getting three, and at the end of the experiment trial, either your event must happen or not happen. Getting four, getting five, getting six. Now I list down six events. Actually, those six events are six outcomes as well. But that is not the end of the events. Can someone give me another event that one can expect? One can expect from this experiment, which is related to the experiment, and that expectation either satis or not satis after the experiment. තකර කියන්න. ඔය ඉවෙන්ට් 6 අර වෙන ඉවෙන්ට් එකක්. So, so by definition, all the outcomes are events. But that is not the end of the story. Because your imagination has no limits. Anyone? Another event, possible event? Those who have learned probability. නිදහසේ නිවාඩු පාඩුවේ ඉගෙන ගත්ත කට්ටිය හදිස්සි එක්සෑම් මතක් කර කර ඉගෙන ගත්ත කට්ටිය මොකද සමහර විභාගෙන එක ඉස්සරහට එන්නේ. විභාගෙට එයිද ඉගෙන ගන්න ඕන බොහොම රිලැක්ස් එකකින්. Anyone? Any event other than these six outcomes or course those six outcomes are events. So event is you think something about that experiment and at the end it will be either success or your expectation is fulfilled or not. I can tell you infinite number of events. ඔගලන්ට තව එකක් තියාගන්න බැරුව ඉතින් මට පුළුවන් ඕන්න ඔගලෝ මැරෙනකන් වුණත් මේකට events කිය කී. Right? So these are some events. Getting an odd number, getting an even number, getting a number which is a perfect square, getting a prime number, getting a number between 1 and 3, right? Getting a number which is divisible by 3. තව ඕනම තව කියන්න. All those are what? Events. Getting 100. It's an event. Right? Why are we interested in events? Actually, we are most interested in events. Why? Why are we really interested in events? Because we calculate probability of events. Or probability of an events order. Right? So we calculate probability of events. So therefore, events are super important for us. Super, super, super important for us. Because we calculate probability of events. What is the probability of getting odd number? What is the probability of getting 2 or 5? What is the probability of getting prime number? So therefore, so event is someone's expectation of an experiment. It must be related to the experiment. Related to experiment. Otherwise, we can't calculate it. Otherwise, if it is not related, maybe the probability of that event will be 0 or infinity or 1. Sorry, not infinity. 0 or 1. Or we can't calculate. So can you give me an event where you cannot calculate probability? Probability, right? I'm not asking other predictions. Saattara, Jyotishane Mangahan. Can you give me an event which probabilistically, that is logically, scientifically, mathematically, we can't calculate for that event? So we call them irrelevant events. Say if I throw a dice, right? If I throw a dice, what is the probability of you passing the exam? So you passing the exam, maybe we can calculate separately, but it has nothing to do with this one, right? Throwing a dice for a logical thinker. දැන් කවුරු කියනවා ඔයා ගිහිල්ලා බාරයක් වෙන්න. කන්න ලව්වක් කරන්න විභාගයට යන්න කලින්. මටත් එහෙම කියලා තියෙනවා. අපේ අම්ම කියලා තියෙනවා අපි ගිහිල්ලා බාරයක් කරමු විභාගයට කලින්. මම ජීවිතේට ගිහිල්ලා නැහැ. Because I know that there is no connection between that and this. exam එකේ result එක තියෙන්නේ මගේ අතේ. මම කොච්චර උද්දර ස්ටඩි කරලා තියෙනවද මම කොච්චර subject එක ගැන confidence එක. Because this has nothing to do with this in my case. Maybe not true correct for your case because you may be talking to gods. You may be getting secret helps, but I'm not getting secret helps. So therefore, for me, this and that has no connection. Okay. Right. So that is therefore we are really interested in events, related events in science, logic, related events. If they are related events, we can calculate probability. Otherwise, of course, we can't calculate probability because those are not related in reality, logically. Okay. So these are all events related to that experiment of throwing a dice. Just some of the events. Remember, all the outcomes are possible events, but it goes beyond that. Okay. And just like you can have compound experiments, you can have compound events that make it even more interesting and challenging. So that make your probability questions more challenging to you also, because your event can also be compound by connecting using logic operators. Say throwing a dice. I'm taking the same example because you can just concentrate on one thing. Throwing a dice is my experiment or the instance of the experiment. So getting odd number is an event. Getting prime number is event. Getting 2 is event. Getting 5 is event. So then what about getting 2 or getting 5? That is also event. So getting 2 is an event, getting 5 is event. I can combine those two with O logic operator. Say getting even number or prime number. Event, composite event. That is why we have some theories, formulas, because otherwise you can't calculate those probability values. Okay. So we can use and or not. Not getting a red ball. Probability of not getting a red ball. Probability of first getting blue ball and then getting red ball. Probability of getting red ball or blue ball. You can see? Now the logic is also coming to the picture. Set is already in the picture. Now logic is also coming because these logic operators are used when we define events. Now you can see the different topics are plugging together. Right, now we'll move on to the fundamental formula of probability. So when we say the word fundamental, that means you don't need to prove it. You don't need to prove it. It is our basis. It's like axiom. Obviously. Obvious thing. Right. So this is the fundamental formula of probability. If you have event A, which is inside the sample spaces, which is inside the sample spaces, probability of event A happening, right? We use the word event. Probability of event A happening is number of occurrences in event A or number of elements in event A divided by number of elements in sample space. So that is called fundamental formula of probability. Okay. So if you take a very simple example, throwing a dice. So your sample space has 1, 2, 3, 4, 5, 6 outcomes because sample space is related to outcomes. And maybe my event is getting 5. So therefore, my event having outcome 5, all the other outcomes are not in my event, but those are in sample space. So therefore, what is the probability of getting 5? Number of element in my event is 1. Number of element in the sample space is 6. Therefore, it's 1, 6. Right? If my event is, because event is my imagination, okay, my event is getting prime number, my expectation. So what are the outcomes related to my event? 2, because 2 is a prime number, 3, 5. But sample space contains 1, 4, 6 as well. So therefore, probability of getting a prime number is number of elements in my event is 3, which is related to the outcomes. Total number of outcomes, so the number of element in the sample space is 6. So the probability is 3 divided by 6. So sometimes, most of the time when we write probability, we just keep as it is. You don't simplify, but some people, they simplify and say half. So your examiner most of the time simplify and keep it as half, but some books, a lot of books just keep it, if it is 3 by 6, they just keep it as 3 by 6. Anyway, it's just a convention, okay? Convention. Now, what happens if your probability or your event goes beyond the sample space? Right? Because your imagination can go beyond the sample space.
Sir,
Yes.
by the way, who came up who came up this proof?
Who came up with?
Proof, this proof?
That is why I told you it's a
Yes.
fundamental formula. So who came up with
Okay.
the idea that 5 plus 2 is same as 2 plus 5? So in the very first day when we did maths in semester 1, I told you math subject is based on three things. What are those three things? Very first day in semester 1, I told this, right? Math subject is, I told you, number one, maths is formal science subject. Formal science subject, 100% we can prove things. There's no doubt. There's no doubt. It's not approximations. Okay. That is why we say formal science. What are the formal science subjects? Maths, computer science, theoretical computer science, okay, probability and statistics. So what are the three cornerstones? One, we have axioms or postulates. Second, we have standards and notations. Third, we have theorems. So we need to prove only theorems. Theorems only we need to prove. So axioms are obviously correct. If it is obviously correct, how can you prove it? That is why we say pratyaksha. තමන් ප්‍රත්‍යක්ෂ කර ගන්නවා මනුස්සයෙක් විදියට. So then we have the standards and notation. Those are just notations. For example, if you write probability of A as PA, it's a notation. Derivative of x squared as d by dx x squared is a notation. Log of 10 as, say, log to the base 10, 100 as this is a notation. 5 into 5 into 5, we can write a notation using this. So if someone asks how do you prove it, there's no proof. This is just a notation. So similarly, this is a sort of a basic rule. Basic rule means axiom. So anyone should understand by yourself this is correct or wrong. Just like whether these two angles are the same or not. It's another axiom, right? No one has proved it. But everyone can see that it is correct. So therefore, this is your question should be not who, of course, that is a valid question, who proved this. So your question, first one is it wrong? If it is wrong, why is it wrong? What are your challenging facts? Okay, because just like you need to think, okay, is it wrong to say that these two angles are wrong? The same, no, right? Of course, if you can prove that these two angles are wrong, then we can get rid of this as axiom and say, okay, this axiom will we no longer use. So therefore, that is why we say fundamental formula. Fundamental formula. Maybe someone has first used it. We don't know, right? Because everything has to be used by someone in the first day, right? Just like finding the fire. But actually, we don't care about the proof because it's fundamental formula. It's like axiom. So everyone should understand it by yourself. Or you need to come up with counter proof, counter examples, and challenge it and discuss with others who accept it as a fundamental formula. Okay, I hope you got sufficient answer. Or you need to come up with now count examples if you want to challenge this.
Okay, sir.
Okay, right. Right. So now what happens if you even go beyond the sample space? Because your imagination can be anything. Your imagination can be anything outside sample space also, right? For example, I so the experiment is throwing a dice. Throwing a dice. So when we say getting odd numbers, you know that the sample space has 1 to 6. Say this is my getting odd numbers, right? So 1, 3, 5, here we have 2, 4, 6. But when your event is getting odd numbers, maybe 7, 9, 11, 13, those are also odd numbers, right? Because you can't say that 7 is not odd number, right? But remember, your event may have values which are beyond sample space. But when you use the fundamental formula of probability, you only consider values within the sample space because others are not possibilities. Those are not possible outcomes. Those are not going to affect your event in this experiment because those are not possible outcomes. So therefore, in reality, if you take it as a general case, probability of your event A happening is number of elements in your event and sample space. A intersection S. That means we restrict it to here, divided by number of elements in the sample space. Okay. Number of elements in the sample space. Sorry. Most of the time we don't mention it, but if you are very precise, that is the real formula, right? Real formula. Because we need to eliminate these because those are not possibility from this experiment. Okay. Right. Right. So these are very simple examples. Just anyway, let's do it. When a dice consisting 1 to 6 is thrown, what is the probability of event getting 6? So your event 6 is only one of the outcome. So therefore, number of elements in your event is 1. How many possible outcomes are there? 6. So therefore, 1 out of 6. Okay. 1 out of 6. Right. Second one, same experiment. What is the probability of getting odd number? Now you must do it knowing what you are doing, not like a machine. Taking your time, go to the basis. Right. So again, number of elements in sample space is 6. So therefore NS is 6. My event getting odd number. So number of outcomes related to my events within the sample space are, or the elements are 1, 3, 5. So that means there are 3 elements like that. So therefore the probability of getting odd number when I throw a dice containing 1 to 6 is 3 out of 6. So now every step you have a justification, right? Formal justification. So that is what we expect from mathematics students who are doing maths. So they are very precise. That is why their confidence is very high. ඒ කියන්නේ ගණන්කාරයෝ කියන්නේ ගණන්කාරයෙක් කියන්නේ එයා අනිත් අය අනුමානයෙන් හිතන දේ එයා precisely දන්නවා. reason එක. ඒක තමයි වෙන්න ඕන. අනිත් අය නිකන් වෙයි කියලා හිතාගෙන කරනවා. මෙයා මේක තමයි වෙන්නේ කියලා කරනවා. මේක ඇප්ලයි කරන්න එපා හැමදැනටම formal fields වලට විතරක් ඇප්ලයි කරන්න. ඒවට ගහකට පෝර දාලා ඉවරලා කියන්න බෑ අනිවාර්යෙන් මේකේ දැන් ගෙඩි මෙච්චර ප්‍රමාණයක් වැඩි වෙනවා කියන්නේ නැහැ. Because that is natural science. දැන් මට ওই ප්‍රශ්නේ වෙලා තියෙනවා. හරි මොකද මම maths නේ. මම ඉගෙනගෙන තියෙන්නේ formal science. මම ඉගෙනගෙන තියෙන්නේ maths. මම ඉගෙනගෙන තියෙන්නේ computer science. මම ඉන්නේ හැමතිස්සෙම formal science වල. ඒතකොට මට සමාජයට ගියාම සමහරවිට මට ප්‍රශ්න ඇති වෙනවා. හරි. ඇයි ඒ? මම සමහර ඒ කියන්නේ මම ඒක තේරුම් අරන් ඉන්නේ දැන්. හරි. දැන් මම හැමතිස්සෙම formal science වල ඉන්න හන්ද මම කොට සමහරවිට බලාපොරොත්තු වෙනවා formal solutions අනිත් පැත්තේ දෙයි කියලා. formal solution අනිත් පැත්තේ දෙයි කියලා. තමන් මට අමතක වෙනවා ආපු එහෙම බෑනේ මේගොල්ලෝ මේ වැඩ කරන්නේ natural science එක්කනේ. නැත්නම් social science එක්කනේ. society එකත් එක්කනේ. nature එකත් එක්කනේ. දැන් මට කියලා කියන්න බෑනේ මේ අපේ පොල් ගස් ටිකක් තියෙනවා මේකට අනිවාර්යයෙන්ම පොල් පළදාව මෙච්චර 100 ගානකින් වැඩි වෙන්න පෝරක් දෙන්න කියලා. හරි ඒක අපේ වත්තර හරි අල්ලපු වත්තර හරි ගිහලා අපේ වත්තර හරි වෙන්න පුළුවන්. හරි. මොකද nature is very complicated. It's probabilistic. Again, it's probabilistic. But formal science is different. 5 plus 2 is always 7. අපි වාගේ වාහනේ කියලා ගෑරේජ් එකකට දැම්ම කියලා. ඔයාලට හදිසි වුණා කියලා ඒක එහෙම හදන්න බෑ. හරි. එතන ඉන්න බාසුන් නැහැ තමයි දන්නේ එතන තියෙන කොම්ප්ලිකේෂන් එක. එතකොට හිතනවා යකෝ software program එකක් ලියන්නේ කොච්චර ලේසිද කියලා. වාහනයක් කැඩිච්ච එක හදනවට වඩා. මොකද මේක මොන හේතුවෙන්ද මේක උනේ කියන එක එයා හොයන්න ඕන කෙරෝලකින්ද. මොකද එයාට පේන්නේ නැහැ එන්ජින් එක ඇතුලේ පේන්නේ නැහැ. ඕල්ටර්නේටර් ඇතුලේ පේන්නේ නැහැ. එයා හිමින් හිමින් මේක අයිසොලේට් කරනවා. මම ඒකනේ කාර්මික වැඩ කරන මිනිස්සුන්ට පුදුම ආදරේ. පුදුම ආදරේ. ඒ මිනිස්සු තරම් මොලේ වේසන මිනිස්සු තවත් නැහැ. අපි හිතනවානේ තමයි බාසුන් නැහැ, පචං ගාගෙන ඉන්නේ. පට්ට මීටර්. මම දොස්තර කෙනෙක්ට වැඩි කල්පනා කරන මේ මිනිස්සු. මේ මිනිස්සු. කල්පනා කරලා තමයි සොලියුෂන් එකක් හොයාගන්න. දැන් මිනිස් සමාජයේ සලකන්නේ නැහැනේ. සමාජයේ සලකන්නේ ඔය නිකන් ඔය පොළ පුරවන, ඇට බෙදන, පාල් පාරුවන්. අස්සනක් ගහලා තියෙන. ඒගොල්ලෝ ඔළුව වෙසන්නේ නැහැ ඇත්තටම. ඔළුව වෙසන මිනිස්සු වෙනම ඉන්නවා සමාජයේ ඕන තරම්. Right. So let's move on to our third example. When a dice consisting 1 to 6 is thrown, what is the probability of getting prime number? So again, number of element in the sample space is 6. So therefore NS is 6. Number of elements in my event, which is related to the sample space, includes 2, or the elements includes 2, 3, and 5. So therefore it is N A is 3. Therefore it's 3 out of 6 again. Okay, 3 out of 6. Right, so you can do this one, right? Greater than 4 means only 5 and 6. Because you don't care about 7, 8, 9, 10. Because we are only interested in the sample space. So therefore 2 divided by 6. Right, now let's look at the properties of probability. What are the properties of probability? Right, probability is always between 0 and 1. Right? Probability is always between 0 and 1. It can't be, there can't be something called probability is 5. Probability is -2. 0 means it's impossible event. That means there are no element in your event which is inside the sample space. No element. It's like your event is a null event, null set. Related to S. Maybe you have elements here, but you don't care about that because those are not going to be outcomes of our experiment. Right? So there must be at least one element here. Then only your probability is not 0. Okay? So that is called when you don't have any element in your sample space which is inside, which is at least one of the outcome, then probability is 0. For example, throw a dice. What is the probability of getting 7? Because 7 is here. So your event is here. So therefore, no elements in S intersection A. So therefore, it is probability 0 divided by 6. Okay, 0 divided by 6. So then what is it? If all your elements in your event are same as your sample space, then it is 1. Can you give me an example of a event which has probability of 1? Anyone? Say, my experiment is throwing a dice. Give me example of an event where the probability is 1.
Getting a number from 1 to 6.
Getting a number from 1 to 6. Right? Or getting a number, because you know that all sides you have numbers. getting a whole number, getting a number between 1 and 100, probability is 1. Because always now probability is not 1. Sorry, okay. Uh, no, correct, right? Always you get a number between 1 and 100. Yes, probability is 1. Because 1, 2, 3, 4, 5, 6 all are number between 1 and 100. Okay. Right. So the probability 1 means it's a certain event. Probability 0 means it's impossible event, logically, probabilistically. And if A is a subset of B, if my event A is a subset of event B, then probability of A must be less than probability of B. That also makes sense, right? Because my B may have additional events, outcomes that increase NB. So when NB is bigger than NA, PB is bigger than PA because NS is the same. Right. I already discussed this, right? Throwing a dice, label 1 to 6. State 3 events where probability is 0. State 3 events where probability is 1. Okay. So getting number 7, getting a number bigger than 10, those are all probability 0. Getting a number between 1 and 6, getting a number, getting a whole number. So those are all probability of 1. Formal logic are once a period. What is mean by formal logic are once a period? It is informal logic. People are formalized using proof. Question is not very clear. What is mean by once a period? So if you clarify, I may answer. Maybe your question is, now when we say formal logic, formal science, okay, let's take it um, broader sense. I don't know whether this is your question. I think maybe this is your question. Now, when we say formal science, I told you that that is 100% comprehensible, 100% provable, right? Maybe your question is, maybe I don't know, my guessing. So, though we call it formal science now, in the future, can it be challenged? And of course, in the past, maybe that was not formal science. Maybe that is your question, right? So what we tell formal science right now was not formal science some times ago, right? Because we were also not intelligent at that time. Maybe in the future, will that be challenged and will they build alternative formal science? So that is an interesting, I don't know whether that is your question. If so, that is an interesting question. Right? Interesting question. It's more philosophical question. Okay, philosophical question. I don't know whether that is your question. Okay. Yeah, that is your question, right? Yeah, that is a very interesting question. And it's a philosophical question because, anyway, it's a long story. I am not 100% qualified to answer that kind of question also because I am not a philosopher like Einstein and those people, right? Russell and those people. So my simple answer is I am not qualified to give you an answer for that kind of question. Maybe you should ask that question from a professor or someone who is in philosophy side. But my gut feeling is, according to the things, because I also had that question, according to my findings, these formal systems are there's another very interesting philosophical question whether maths is discovered or invented. This is a very interesting question. Now you know that people invent things, right? People invent things. like telephone. And some people discover things. Like, for example, Newton discovered that there's a connection F equal ma, which is not 100% correct, but reasonably correct. So that is not invented, that is discovered. Right? Some things we invent, like technology. Now, maths, when we say Pythagoras theorem, is it invented or discovered? Because that theorem should, that connection should have been there forever, right? But someone need to find it. Someone need to find it. But once you find it, it's formal thing, not like F equal ma, because this is perfectly correct. So therefore, so this is according to our brain, our knowledge system. According to our brain, our knowledge system, this is our formal knowledge. Maybe for a different type of a life species, they may have their own formal knowledge system, formal science, which may contradict with our one. But for us, for humans, for current generation, this is our formal science, which is unchallengeable, at least by our way of thinking, our way of logical reasoning. Okay, so that is the short answer. It's more philosophical question. Okay, because we don't know whether there are parallel universe and there are alternative systems. Okay, knowledge systems. Right. So that's the those are the properties of probability. Probability is always between 0 and 1, and probability of event A is lesser than probability of event B if A is a subset of B. So then we have the probability of complement events. So if you know the probability of event A happening, let's call it PA, then probability of event A not happening is 1 minus PA. Again, use your common sense to prove it by yourself. It's axiom. The probability of getting 6 is 1/6. And what is the probability of not getting 6? 1 minus 1/6, which is 5 divided by 6. Because not getting 6 means you get in 2, 3, 4, 5. 1, 2, 3, 4, 5, which is 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6, which is 5 over 6. So therefore, yes, this rule works. This rule works. So PA bar is 1 minus PA. Okay. So that is again, you need to convince yourself by your own logical thinking. Right. Now we'll move on to mutually exclusive events and probability rules related to mutually exclusive events. Now make sure you pay attention to these word events. Right. Mutually exclusive events. First of all, you must know what is meant by mutually exclusive event. Then do we have probability related rules or formulas to use that kind of situations and calculate probability? Because you have learned this, right? This is something you have learned in your O level. මම දන්නේ ඔයගොල්ලෝ සිංහලෙන් මොකද්ද ඉගෙන ගත්තේ කියලා අපි ඉගෙන ගන්න කාලේ නම් මම ඉගෙන ගත්තේ O level මීට අවුරුදු සෑහෙන කාලයකට කලින්නේ. මේකට කියනවා අන්‍යෝන්‍ය වශයෙන් බහිෂ්කාර සිද්ධි කියලා. මම දන්නේ දැන් කියන්නේ කොහොමද කියලා. ඔයගොල්ලන් දැන් උගන්වන්නේ කොහොමද සිංහලෙන්? මොන සිද්ධි කියලාද මේවට කියන්නේ? Same word to something else. I don't know. එහෙම නැති කියන්නේ නැද්ද ඒක? ගොළු භාෂාවෙන් දිගන්නේ. නමක් නැතුව දිගන්නේ. Right. So what is mean by mutually exclusive events? Remember, these are events. Events are our imaginations, our expectations. Can someone tell me what is mean by mutually exclusive event? ඕගොල්ලන්ගේ භාෂාවෙන් මම දන්නේ මම හිතන්නේ ඕගොල්ලන්ගේ භාෂාවෙන් සිංහලෙන් කරපුවාට මම දන්නේ මම හිතන්නේ බහිෂ්කාර සිද්ධි කියලා දන්නේ නැහැ කියන්නේ වෙන මොකක් කරනවක් තියෙනවද දන්නේ නැහැ. What do you mean by two things? Because now you need to use the words I gave you, right? Experiment, event, trial, outcome, sample space. ඔය වචන පාවිච්චි කරලා කියනවා things කිව්වම මම දන්නේ නැහැ නේ. things කියන්නේ event එකකටද, outcome එකකටද, experiment එකකටද? දැන් උතේ precise වෙනවා කියන්නේ. things කිව්වම මම දන්නේ නැහැ මම කොහොමද දන්නව things කියන්නේ මොනවටද කියලා? දැන් ડોක්ටර් කෙනෙක්ට කියන්න පුළුවන් අන්න අර මට අරකට දෙන්න කියලා. මේ දැන් ડોක්ටර් කෙනෙක් මෙතන ලොකු සර්ජරියක් කරනවා. හරි. එයා ලොකු වගකීමක් දරන කෙනෙක්. එයාට කියන්න පුළුවන් එයාගේ වටේට ඉන්නව නේද? සහයට කට්ටිය. මේ මට අරකට දෙන්න කියන්න පුළුවන්. අරකට දෙන්න ගමන් හරි මොකක් හරි දෙයිද? එතන තිබුණොත් එimhe ඩස්ට්බින් එක දෙන්න පුළුවන්. අරකට නෙල්ලියෝ. So if you want serious responsibilities in your life, try to be very precise. Now can think කියන වචනේ අයින් කළ බලන්න උත්තර දෙන්න පුළුවන්. Yes, that example is correct. Right. So mutually exclusive, we say that two events are mutually exclusive, right? Or the easier word is disjoint. Right. සරල වචනේ තමයි disjoint. Right. Mutually exclusive only බරයි. Right. So we say that two events are mutually exclusive if none of the outcomes satisfy both events. If none of the outcomes satisfy your two events, then your two events, your expectations are mutually exclusive. Simple as that. Now, පාවිච්චි කරේ අර වචන සෙට් එක විතරයි යා. If you have two events and none of the outcomes of an experiment belong to both the events, your two events are mutually exclusive. දැන් මම things අනම්මනම් කිව්වේ නෑ. පොඩි things කවම මම දැන් කාටවත් ඉදාගන්න මොනවද මේ things කියන්නේ කියලා. හරි? Right. Another very important objective of learning maths is make you a very good communicator, very precise communicator. මේක ඇතුළේ මම කොයිවත් things පාවිච්චි කරන්නේ නැහැ. Two or more events are mutually exclusive or disjoint if those events, right, those two events or more events do not occur at the same time. ඒ event දෙකම එකට වෙන්නේ නැහැ කියන්නේ මොකද්ද? එක outcome එකක් මේ දෙකම වෙන්නේ නැහැ. event දෙකම එකට වෙන්නේ නැහැ. කියන්නේ outcome එක ගත්තට පස්සේ මේ event එකයි දෙකම satisfy වෙන්න විදියක් නැහැ. Right? For example, getting odd number, event A, getting even number, event B, those are mutually exclusive because none of the outcomes will satisfy both events. If you get to 5, it's in event A but not in event B. If you get 6, it's in event B but not satisfy event A. Okay. That means both events will never satisfy together for a given outcome. Okay. So that means there are no common outcomes. So there are no common outcomes that satisfy both events. No such things. So those are disjoint sets. So if those two events are disjoint or mutually exclusive, if you want to find the probability of event A happening or event B happening, O, you know that O means union in sets. The probability of event A happening or B happening is probability of A plus probability of B. So that is formula we can use. How do you prove that? Because probability of A union B is number of elements in A union B divided by number of elements in sample spaces. Number of elements in A union B when they are mutually exclusive is number of elements in A plus number of elements in B. That we can write it as NA divided by NS plus NB divided by NS. and this is PA, and this is PB. So that is the proof. Then we proof then so make fundamental make this is not the fundamental theorem of probability, right? Make the proof now using sets. Make proof steps per second again. So I write this on the assumption that A and B are mutually exclusive or disjoint. So therefore we have formula. You can simply add the probabilities. If you are looking for the probability of A or B happening, and it works for C, D, right? Any number of events as long as they are disjoint. Then what happens if they are not mutually exclusive? Yes, we can calculate the probability for that also. Right, so this is an example for mutually exclusive events, okay? So when a dice is thrown, what is the probability of getting odd number or getting 6? Remember, these are mutually exclusive. Why? None of the outcome will satisfy both. If you get 1, this is satisfied, not this. If you get 2, none of these are satisfied. That is fine. If you get 3, this is satisfied. If you get 4, this is satisfied, but not this. If you get 5, this is satisfied, but not this. If you get 6, none of these are satisfied. So the prerequisite is none of the outcome must satisfy both. Then these are mutually exclusive. So therefore, PA, probability of this plus probability of this is 3 out of 6. Probability of this is 1 out of 6. So therefore, probability is 4 out of 6. Okay. So if those are not mutually exclusive, that means they are joint. That can happen. So that means there are some outcomes which satisfy both event A and event B. Right? Like getting odd number is my event A. Getting prime number is my event B. Remember, there are numbers which are both odd and prime, like 3, 5. So then these are not mutually exclusive events. Because some outcomes satisfy both. Right? I always use the word outcome, right? Event, right? ඒ වචන සෙට් එකේ තමයි මම ඉන්නේ. මම කොයි වෙලාවත් things අනම් මනම් කියන්නේ නැහැ. ඔයගොල්ලෝ ඒකෙන් අයින් කරගන්න මේ හදන්නේ. ප්‍රිසයිස් කරන්න හදන්නේ. Right. You know that if it is two sets are not joint or disjoint or they are joint, number of elements in A union B is NA plus NB minus NA intersection B, because this double count must be adjusted because this value is counted here and here. You must adjust it by subtracting. And now if I subdivide by NS, NA union B divided by NS, that is what PA union B is NA divided by NS plus NB divided by NS minus NA intersection B divided by NS. That is probability of A plus probability of B minus probability of A intersection B, both A and B happening. So you need to subtract. Okay. Of course, if A intersection B is null, then this becomes the previous formula. Okay, because then it is disjoint. Right, so this is an example. When a dice is thrown, what is the probability of getting an odd number? O. Remember, union means O. Getting a prime number. So odd number, what are the possible values? 1, 1, 3, 5. Say A. Let's call B the prime number. 2, 3, 5. Now you can see 3 is common, 5 is common. So therefore, this is not mutually exclusive. Now we need to say PA union B is PA plus PB plus, so PB minus PA intersection B. Probability of A happening is 3 out of 6. Probability of B happening is 3 out of 6. Probability of both A and B happening, that is you have 2 outcomes like that. 2 out of 6. 4 out of 6. So final answer is 4 out of 6. Is it clear? හදිස්සි වෙන්න එපා හිමින් කරගන්න. හරි. හදිස්සි වුණාම තමයි ප්‍රශ්නේ වෙන්නේ. හදිස්සි වෙනවා. මොකද ඔයාව හදිස්සි කරන්නේ හැමතිස්සෙම විභාගේ. හරි විභාගේ. මොකද හැමතිස්සෙම සබ්ජෙක්ට් ඉගෙන ගන්නවට කලින් විභාග ඉස්සර වෙන්න පටන් ගන්නවා. එතකොට අර ටයිම් එක ස්පෙන්ඩ් කරන්න බෑ ඔයාලට. Now we move on to our next second concept, independent events. Now a lot of students mix these things together. So they don't understand the difference between mutually exclusive events and independent events. So it's very important that you understand the difference. Right. So remember, mutually exclusive events means two events where none of the outcomes will satisfy those two events. Right. So then what is meant by independent events? So the word itself is independent, nidahas. So independent events means one event does not affect the other event. Okay. So those events are due to independent trials, independent experiments. Okay. For example, throwing two dices. So I throw one dice and I throw another dice. So obviously throwing this dice and this dice are independent. Outcome of this is not going to affect the outcome of this. Or tossing the dice twice. First time you throw it and find the value. And then you again throw it. So second attempt is independent from first attempt. Or tossing a coin 2 times. Or tossing a coin and throwing a dice. So tossing a coin is not going to influence by throwing the dice. Throwing a dice is not going to influence by the result of the coin. Or taking a ball from a bag with replacement. So you take a ball and put it back and you take it again. So the second outcome is not going to depend on the first outcome because again you have all the balls. So those kind of things are independent events. Okay. So that means there are dependent things also. Right. If they are independent, PA intersection B, that means both A and B happening. Earlier, mutually exclusive, we discussed A or B happening. Now A and B happening is PA into PB, multiply. That means that happens and this happens. Okay. So classic example is you throw a dice and toss a coin independent because this outcome not going to affect this, this outcome is not going to affect this. Say, what is the probability of getting 6 and head? Now independent, right? Because getting head is independent from getting 6. Getting 6 is independent from getting head. So what is the probability of getting 6? 1, 6. What is the probability of getting head? Half. And what is the probability of getting 6 and head? You can multiply. 1 out of 12. Okay. So that is how we work with independent events. So we can think of this as a compound event, but it consists of independent sub-events. Okay. And it works for any number of independent events. We have another event, so then you can keep multiplying. Okay. And remember, this formula is always correct. PA union B is PA plus PB plus PA intersection B. Now, if A and B are independent, then PA intersection B is PA into PB. So therefore, this is PA intersection B. If A and B are independent event, PA union B is PA plus PB minus PA intersection B. Right? So don't just remember this one, remember this one also. For example, say, again, let's look at the same experiment. Getting 6, getting head. Getting 6, 1, 6. Getting head, half. What is the probability of getting head and 6? 1, 6 into 1 half, 1 12. Then what is the probability of getting head or getting 6? Getting 6 or getting head. Okay. So is it 1 6 plus 1 half? No. Probability of getting 6 is 1 6. Probability of getting head is half. Then you need to subtract 1 12. So that is your probability of getting head or getting 6, which is out of 12, 2 plus 6 minus 1. 9 out of 12. 9 out of 12. Okay. Is it clear? Now, this is sometimes you get confused, okay? So this is probability of A and B happening. This is probability of A or B happening. You can double check this also, whether we get 9 out of 12. If you write down the sample space, we got 9 out of 12, right? 1 head, 2 head, 3 head, 4 head, 5 head, 6 head. 1 tail, 2 tail, 3 tail, 4 tail, 5 tail, 6 tail. So getting 6 involves this and this. Or getting head, that includes this. Okay. And these two, this is also taken, but it's already counted. So now how many times? 1, 2, 3, 4, 5, 6. Is it 7? PA is 1, 6. PB is half minus 1 over 12, right? 12, 2 plus 6 minus 1. So 6 plus 2 is 8. 8 minus 1 is what? 7. Not 9, 7. 1, 2, 3, 4, 5, 6, 7. Correct, right? So the answer is correct. And double check. Right? So therefore, when we have independent events, we not only have a formula for PA intersection B, which is PA into BB. We have formula for PA union B also. That is PA plus PB minus PA into PB. That is coming from this general formula. Okay. General formula. Is it clear? Because sometimes you get confused about independent events, mutual exclusive events, right? I told you this is a sort of a touch subject. Touch checking in there. වාහනයක් එලවන පීනනවා වගේ තමයි. Confidence එක තියෙනවා. Subject එක. ඒකයි. That is why you need to be very serious about the basics. Right. So we did this example. Right. So you may have seen a lot of questions that you do using tree diagrams, Rooksatahan. Tree diagram. A lot of students they don't know that actually when we use tree diagram, most of the time what we are doing is probability questions related to independent events. And why you are multiplying? Because that is the formula of independent events. Sometimes students have no idea about the independent events and this tree diagram. Actually, we use tree diagram because these are independent events and we can multiply it. Say we have a bag of balls. Say 2 blue balls, 3 red balls. So we take one ball and replace it and again take another ball. So the moment you replace it, those are independent. Right? So therefore, what are the possibilities? First time you get blue, second time you get blue. First time you get blue, second time you get red. First time you get red, second time you get blue. First time you get red, second time you get red. So there are 4 possibilities: blue, 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 red, red, blue, red, red. Because these are independent, we can multiply. So a lot of people multiply, but they don't know that, or they don't care that you multiply because these are independent. Because taking second ball is independent from taking first ball because you replace it. So therefore, what is the probability of getting blue and blue? 2 out of 5 into 2 out of 5. What is the probability of first one blue and second one red? 2 out of 5 is the first one blue. 3 out of 5 is the second one red. So therefore 6 out of 25. So this is getting red, blue, red, red. So that is why how you get it. Basically, when we use tree diagram, why we multiply here? Because those are independent events. Second take is independent from first take. And if your question is getting blue and blue, blue and red, you can just multiply this probability into this probability. Okay. But you can do it if it is with replacement. Why? When you replace, only the second one is independent from first one. If you don't replace, what happens? Then second one depends on the first outcome. Second outcome depends on the first outcome. So then it is not independent events. That is where you need to use conditional probability. Right? Second event depends on the first event. Right? Do this as exercise. Both find PA union B and PA intersection B. Okay. Of course, PA union, it says independent. Independent. So because it says independent, PA union B, first you can find PA intersection B, which is 0.5 into 0.48. That is 0.24. Now you can find PA union B. That is PA plus PB minus PA intersection B. And PA is 0.5, PB is 0.48, and PA intersection B, because they are independent, PA into PB, 0.25, 24. 0.98 minus 0.24. Is it 0.74? Yes, it's 0.74. Okay. Right. Right. Is it clear? Because now we have two major concepts: mutually exclusive events, independent events. So now we move on to our third concept, conditional probability. Conditional probability. So far we discussed just the probability. Getting 6, getting head, getting a red ball. But now we are going to look at events which has a condition also. Okay. So given that you have got an odd number, say you throw a dice. So what is the probability of getting 6? 1 out of 6. Then what about this? What is the probability of getting 6 given that you have got a even number? 6 ලැබීමේ සම්භාවිතාව 6 එකයි. දැනට ඔයා දන්නවනම් ඔයාලට හම්බෙලා තියෙන්නේ ඉරට්ට සංඛ්‍යාවක් කියලා. 6 වීමේ සම්භාවිතය. Super easy, right? It's 1/3. But let's define a formal formula. You can use common sense and say, right? ඉරට්ට සංඛ්‍යාවක් නම් හම්බෙලා තියෙන්නේ මේ විදිහ හම්බෙලා තියෙනවා කියලා අපි දන්නවා either 1, 2, 4 or 6. So out of 2, 4 or 6, what is the probability of getting 6? 1 out of 3. That you can use your common sense, logical thinking. But let's define a formal formula. So we have a notation for that also. This is called probability of B given A. Conditional probability of event B happening given that event A has happened. Okay. So that is number of elements in A intersection B divided by number of elements in A. So usually probability of B is number of elements in B, or very formally number of elements in B intersection S, right, divided by number of elements in S. Now when we have the conditional probability, why do we need to change it like this? So why, now you need to explain why my NB, or formally this is NB intersection S. S sample space divided by NS. Now, why is it NS become NA? Common sense, logical thinking. Because earlier we remember when you take probability, you need to find out all possible number of all possible outcomes. But now we say that A has already happened. If A has already happened, now all the possible outcomes are not belong to anything here. Because it says A has happened. Therefore, now our sample space is restricted to number of elements in or elements in A. Because your condition says A has happened. So therefore, these things can't happen. So therefore, now my new sample space is A. So therefore, number of elements in our new sample space is NA, not NS. So then earlier we took, remember we are interested in probability of B. Earlier we took number of elements in B here. Right? Number of elements in B or number of elements in B intersection S. That is when our sample space is S. Remember when our sample space is S, we never took anything outside S. Because that doesn't make sense. Now, because our new sample space is A, we don't need to take anything outside A. We need to take only those belong to B, but inside A. Earlier, we just took only inside S. Now this is our new S. So therefore, you need to take only those who are in the B, but inside A. So therefore, A intersection B. Those belong to B, because probability of B, but inside A, because A has already happened under the condition A. So therefore it is NA. Sorry, NA intersection B. Right? NA intersection B. And if I divide both sides by NS, it is PA intersection B divided by PA. Because NA divided by NS is PA, NA intersection B divided by NS is PA intersection. So that is why we get this formula. Probability of B given A is probability of B intersection A divided by PA. Or in other words, we can cross multiply and say PA intersection B is PA into PB given A. So this is also useful, and this format is also very useful. So you need to remember both, but you must remember after this understanding, how do we get this? What is the logic behind this? So these are not fundamental theorems. These things you need to prove yourself. So if I tell it to someone else, I am obliged to prove it, explain it, give a logical explanation. And if you are using it, you must prove yourself. Okay? This is pretty much common sense, right? Probability of B given A is probability of B intersection A divided by probability of A. Okay? Because you get it from here. And when you cross multiply, PA intersection B is PA into PB given A. Now, this is an interesting one. This is something like independent events, right? In independent events, PA intersection B is PA into PB. But if it is conditional probability, right? So then PA intersection B is PA into conditional probability of B. Right? So again, you can multiply. But because here we multiply because of this conditional probability rule. So that is why when the two events are independent, still we can multiply. But that time we multiply because of this rule. රුක් සටහන් වල අපි බෝලේ දැම්මමත් වැඩි කරනවා. බෝලේ ඒතකොට ඉන්ඩිපෙන්ඩන්ට් නැත්තා. බෝලේ දැම්මේ නැති වෙලාවෙත් වැඩි කරනවා. ගොඩක් අය හිතනවා කොහොමද බෝලේ දාද්දිත් වැඩි කරනවා. බෝලේ දාන්න නැතුව ඒතකොට මේ බෝලේ දාද්දි වැඩි කරන්නේ එක ඉන්ඩිපෙන්ඩන්ට් ඉවෙන්ට්ස් අන්ට. බෝලේ රිප්ලේස් කරාම ඒත් වැඩි කරනවා. එතකොට මේ රූල් එක අනුව කන්ඩිෂනල් ප්‍රොබබිලිටි රූල් එක අනුව. එතන වැඩි කරද්දී අපි දෙවෙනි ප්‍රොබබිලිටි එක ඇඩ්ජස්ට් කරලා තියෙනවා. කන්ඩිෂනල් ප්‍රොබබිලිටි අරන් තියෙනවා. ගොඩක් අය මේක එහෙම හිතන්නේ නැහැ. ඔය මැෂින් වගේ පාඩම් කරනවා. ඒ කියන්නේ රුක් සටහනයි ඉන්ඩිපෙන්ඩන්ට් ඉවෙන්ට්ස් අතර සම්බන්ධ බලන්නේ නැහැ. රුක් සටහනයි කන්ඩිෂනල් ප්‍රොබබිලිටි එක අතර සම්බන්ධය මොකද දෙකටම අදින්න එකම රුක් සටහන. හරි. ඉන්ඩිපෙන්ඩන්ට් වුණාම රුක් සටහන අදිනවා කන්ඩිෂනල් වුණාම රුක් සටහන. ඒ දෙක ගලපන්නේ නැහැ මේ ෆෝමියුලාස් දෙකට ගොඩක් අය. Right. So these are conditional probability questions. There are 2 blue balls and 3 red balls. So your bag has 2 blue balls, 3 red balls. Balls are taken randomly without replacement. So that means second time take depends on the first time. So therefore it's a conditional probability. So the first take is super easy, right? Because what is the probability of getting blue? 2 out of 5. What is the probability of getting red? 3 out of 5. Okay. But now second take. If you have already taken blue, you have only 1 blue ball and 3 red balls. So then what is the probability of getting blue? 1 out of 4. Probability of getting red? 3 out of 4. If your first take is a red, now you have 4 balls, 2 red, 2 blue. And what is the probability of blue? 2 out of 4. What is the probability of red? 2 out of 4. And of course, if you want, you can keep taking, but let's finish like that. So then what is the probability of blue and blue? That is probability of B1 intersection B1. That is probability of, sorry, B2. V1 into probability of B2 given B1. Right? Remember that formula? The second form of the conditional probability rule? Probability of A into probability of B given A has happened. Probability of B1 into probability of B1 given, sorry, B2 given B1 happened. That is probability of B1 into B2. So that is why here also we can multiply. 2 divided by 5 into 1 divided by 4. And the answer is getting blue is 2 divided by 20. Here we multiply not because they are independent, because conditional probability also this formula work. But this time remember this is not 5. This is adjusted because this is not probability of B2. This is the probability of B2 given B1. That is why this is not 1 out of 5, rather 1 out of 4. So therefore, this is adjusted probability. This is conditional probability we have written. So that is why we can multiply, because conditional probability rule also gives you the multiplication. So therefore, yes, we draw the tree diagram for both independent and conditional, but yes, we can multiply, but remember you use the conditional probability values, because this time we are using this rule. So knowing do it. දැනගෙන වැඩේ කරන්න. හරි. නොදැන ඔහේ පිස්සෝය ගණන් හදන්න එපා. පිස්සෝය ගණන් හදන්න ඔයාලට ප්‍රෙෂර් එක වැඩි. හරි. ඇයි නොදන්න නොතේරෙන නොදන්න මගුල් කරනවා. එහෙම කරා කියලා ජීවිතේ කන්ෆිඩන්ස් එක බිල්ඩ් වෙන්නේ නැහැ. යමක් කරන්න කියලා. දැන් ලොකු ප්‍රශ්නයක් නේද? ගොඩක් අය ඉගෙන ගන්නවා, ඉගෙන ගන්නකොට රස්සාවක් කරන්නේ. තමන්ගේ වෘත්තියකට යන්නේ නැහැ. සමහර මේ IT ඩිග්‍රියක් ගන්න මොකටද? ගෙදරින් කියන හන්දා. යාළුවොත් කරන හන්දා. ඊට පස්සේ IT ඩිග්‍රියක් අරගෙන මොනවා හරි වෙනේම කරාට මගේ කිසි අවුලක් නැහැ. හරි කැමති දෙයක් ඔයා කරන්න. ඇයි ඒ? Tamanට එහෙම ඩිග්‍රියක් ගත්ත පළියට වැඩක් කරන්න පුළුවන් කියලා ඇඟට දැනෙන්නේ නැහැ. ඇඟට දැනෙන්නේ තේරුම් ගත්ත කට්ටියට යන. තේරුම් ගත්ත කට්ටිය. ඒගොල්ලෝ දැනනවා හරි මට දැන් මේකෙන් මොනවා හරි කරන්න පුළුවන්. මොනවා හරි නෙමෙයි. සීරියස් වැඩක් කරන්න පුළුවන්. I can doing some serious web development, mobile development, database design, data analysis. I can train a AI model. So you should feel like that. You get that feeling when you understand subjects. Right? Not because you passed exams. Because I'm telling this my experience. In the final year, there are students, more than 50% of the students, they have no idea how to develop the software. Right? When they encounter a problem, they don't know how to solve it. Right? Because they have not used to practical thinking, practical problem solving. They were so busy preparing for exams, passing exams, okay? Rather than understanding subject. Okay. Right, do this quickly. I think this is one of the past paper questions. Quickly do it, take 2 minutes. And first identify what kind of a question am I looking at. So what kind of techniques I'm going to use? Am I going to just use formulas? Am I going to use some sort of a graphical technique? If it is a graphical technique, what is the connection between the technique and the formula? Is it independent event? Is it conditional probability? Is it mutually exclusive? Is it a simple problem? Is it and? Is it or? Okay. Six-sided fair die numbered from 1 to 6 and a four-sided fair die numbered from 1 to 4 are rolled simultaneously. Right? The probability of getting total of two face values is 4 or less, given that both face values are different. Right? Both face values are different. Now, this is not a very straightforward question, right? Very straightforward because it has a bit of independent events is there, bit of conditional probability is there also there. Okay, the way the question has been asked. Right. So the best thing is maybe we can draw a tree diagram, right? Six-sided fair die numbered from 1 to 6. So that means you have 1, 2, 3, 4, 5, 6. Getting 1, getting 2, getting 3, getting 4, getting 5, getting 6. Four-sided fair die numbered 1 to 4. So when this is 1, this can be one of the 4. Okay. So again, it can be 1, 2, 3, 4, but it's independent. Okay. Because we throw it simultaneously. Probability of getting, so therefore, what are the possibilities? 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, and so on, right? So the question is, and also what is the probability? This is 1/6. This is 1/4. Everywhere 1/6, 1/6, 1/6, 1/6, 1/6. Everywhere it is 1/4, 1/4, 1/4, 1/4, 1/4, 1/4. Okay. So therefore, one particular possibility is 1/6 into 1/4. That is 1/24. For any of this, it is 1/24. Remember, when you add these things, it must be 1. Because there are 24. Right? Right. Now the question is, probability of getting the total of two phases is 4 or less. 4 or less. 4 or less means this is one possibility. This is one possibility. This is one possibility. But this is not going to work. This is another possibility. This is another possibility. Then this is another possibility. Others are not possible, right? Because 1 plus 1, 1 plus 2, 1 plus 3, 2 plus 1, 2 plus 2, 2 plus, 2 plus 1 and 2 plus 2, and 3 plus 1. Okay. So if they ask simply what is the probability of getting 4 or less, you just add that is 1 out of 24, 1 out of 24, how many times? 1, 2, 3, 4, 5, 6. That is 1 out of 24, 6 times. That is 6 out of 24. But that is, if the question is only this, but it says, given that both phase values are different. So now there's additional restriction. Both phase values must be different. So therefore now we need to eliminate 1, 1. We need to eliminate 2, 2. Okay. We need to eliminate 2, 2. So therefore now what are the values? We have how many possibilities? 1, 2, 3, 4. And each time it is 1 over 24. That is 4 out of 24, right? 4 out of 24. C. Okay. See, 4 out of 24, 4 out of 20. Let me double check. So we need to eliminate these things. 2, 2, 1, 1. Yes. 1, 1, 2. Yeah. So now we need to eliminate not only 1, 1, 2, 2. We need to eliminate 3, 3 also, right? 4, 4 also, because those are same values. But nothing here because 5 and 5 is not there, 6 and 6. So therefore, we need to eliminate 1, 1, 2, 2, 3, 3, 4, 4. So that means altogether, how many we have? 20. Because out of 24, we need to eliminate those 4. Then how many possibilities are satisfying our condition, our requirement? That is this, 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 this. That is 1, 2, 3, 4. So therefore, 4 out of 20. Answer is 4 out of 20. 4 out of 20. Okay, because we need to eliminate these possibilities. 1, 1, 2, 2, 3, 3, 4, 4. So then altogether we have only 20 possibilities. Out of those 20 possibilities, 4 of the possibilities satisfy our condition. So therefore it's PA divided by PA intersection B. So the PA intersection B divided by PA. So the answer is 4 out of 20. 4 out of 20. So it's a challenging question, okay? It's a challenging question. So you need a bit of experience, exposure, and a lot of concentration. I also forgot about eliminating those from sample space, okay? Right. 4 out of 20. Right, now we move on to our final subtopic in your syllabus. Of course, there are some more concepts in probability, some more concepts, advanced concepts. But this is usually the normal level we go in unless you are doing maths degree. Of course, those who are doing maths degree, they learn 100% maths, okay? So now think about those who are doing a degree which is maths special, what kind of fun they are having, right? There are students, so they do maths. So usually they do only 4 subjects, and out of 4 subjects, maybe 2 or 3 subjects are maths related, maths, statistics. So obviously they go beyond this, right? Right. So you guys, actually what we learned today are pretty much all your maths. So don't think that you are learning very advanced maths, right? So if you are doing a degree in maths, that degree has nothing to do with the A-level maths also. Okay. Just remember this, right? If you do a degree or if you do engineering subjects, so in engineering, because I did engineering, we have maths in all 4 years. All 4 years we have maths. And none of these things are either O-level maths or A-level maths. So in the university, the first year, semester 1 start with something beyond what we learn in A-level maths. Because that is why they only take math student for the engineering. Math student for the engineering. And of course, if you do a special degree or degree in mathematics, obviously they are not going to do A-level things, right? So therefore, don't think that this is very difficult, right? Because I can still remember when I first joined my first lecture in maths in my university, our subject was partial derivatives. Partial derivatives, because in A level we have already done this. So the very first day, semester, at that time, there's nothing for semester 1, semester 2, first year. Very first lecture was about partial derivatives, something like DABA, right? Partial derivatives. Because we had already done derivatives in A level. So therefore they don't do any A level maths in university. So they start from where we stopped in A level and go beyond that. And still I can remember I did not understand a single statement of what is it. I didn't even understand what is meant by partial derivatives also. during the lecture. So don't think that you are learning very advanced things, okay? No, you are just learning O-level things, right? And this is, I think, this is the only thing that is beyond your O-level from your probability topic, okay? Now the thing is, if you go into the industry, say as a software engineer, right, data scientist, you can't say that I have done my BIT, I know only this kind of maths. Maybe this guy who is sitting next to you, who is also a software engineer, who is also a data scientist, who is also AI engineer. Maybe he has done A-level maths, maybe he has done engineering degree. So you can't say that I am mama අහිංසකයි මම එච්චරේම ලොකුවට කරන්න දෙයක් නැහැ ඉතින්. So he also has a potential, right? You need to match with his potential, right? Because when you are in the same team, right? Team එකක් ඇතුළේ ඉන්නකොට ඒ අනිත් අය හිතන විදිහට ඔයාලට හිතන්න පටන් ගන්නවා. ඒක නිසා කියන්නේ පුළුවන් තරම් දැන් මේවා සීරියස් අරගෙන ඉගෙන ගන්න. එහෙම කරන්න ඕන නම්. එහෙම නැත්නම් එහෙම නැති තැනක ජොබ් එකක් කරන්න. එහෙමයි ඉන්නේ නැති, එහෙමයි ඉන්නේ නැති. Right. Bayes theorem of probability. This is our last topic. But if you are comfortable with these things, and if you have willingness to learn some more things, right, by your own, for example, finally there's a math subject, but very rarely students select that math subject. Very rarely. So they don't attend the sessions. They because it's optional subject. So they do some other theory subject and but when if you go to the industry, so there are plenty of students, plenty of professionals who know those concepts. So then they will shine, right? They will shine. Their thinking power will be higher. So they will solve problems faster than you did. Right? So they will come up with more. They will handle more complex situations. So you need to get into the same level as much as possible. එහෙම කියන්න බෑ මේව අමාරුයි කියලා අඬනවා. මේ O level maths. Right. Bayes theorem. So before moving to the Bayes theorem, you need to understand what is mean another small concept. What is mean by exhaustive events? So then only we can discuss about Bayes theorem. Right. It's super simple concept. If you have set of events, okay. Right. If you have set of events, of which one will definitely occur whenever the experiment is performed, is called exhaustive events. What is that? What is the meaning of that? So that means you have set of events. Say event 1, event 2, event 3, and so on. At event 4. Now, when we do experiment, you get outcomes. And you get outcomes. If every outcome belongs to at least one of the events, then we say our events are exhaustive. Now, we have covered these possibilities, event 1, event 2, event 3, event 4. But what happens if there's outcome like this? This outcome is not belonging to E1, E2, E3, E4, right? So then your events are not exhaustive. Your events are exhaustive if you have maybe another couple of events, say event 5, event 6. Now if there's a particular outcome, say this outcome, it belongs to this event. This outcome, it belongs to this event. So every outcome belongs to at least one event. So then we say that your events are exhaustive. Okay? If your events are exhaustive, its union is sample space. Earlier union was not sample space, right? Because when you have something like this, your union has not covered this part. But now, say E5, E6. And of course, your events can be something like this also, right? Event 1, this is event 2, this event 2, this event 3, middle part is event 4, this is event 5, and this is event 6. So now also my events are exhaustive, because if you take any point, it belongs to one or more events. Sometimes now it belongs to one or more events. So this outcome belongs to event 1 and event 2. This belongs to event 4, event 6. Okay. This belongs to event 6 and event 5. So therefore my events here are also exhaustive. Here also exhaustive, but here it's exhaustive and mutually exclusive. Here exhaustive but not mutually exclusive. Right? Not mutually exclusive. Here mutually exclusive but not exhaustive. Now event E1 and event E2 are mutually exclusive but not exhaustive, because these outcomes does not belong to any of these. So therefore there are three possibilities, right? Mutually exclusive events, but maybe they are not exhaustive, right? Exhaustive events, but maybe they are not mutually exclusive. Third possibility, we have set of events which are exhaustive at the same time mutually exclusive. Something like this. Is it clear? Is it clear? So exhaustive and mutually exclusive, two different concepts. So therefore there can be situations both mutually exclusive and exhaustive like this. Mutually exclusive but not exhaustive. Exhaustive but not mutually exclusive. And there can be situations where not mutually exclusive and not exhaustive. That is the fourth possibility. This is not exhaustive because these outcomes does not belong to event 1 or event 2. And of course, they are not even mutually exclusive as well. So those are the four possibilities, right? Is it clear? So mutually exclusive means none of the outcome will satisfy more than one event. That we have already discussed, right? None of the outcome will satisfy more than one events. So then those events are mutually exclusive. Like if my two events are getting odd number, getting even number, those are not mutually exclusive. Sorry, those are mutually exclusive because none of the outcome will satisfy both. That is why we say when mutually exclusive, there is no uh, common area. Right? Common area like this. Now, this is not mutually exclusive, but this is mutually exclusive. None of the outcome will satisfy both more than one event. That is mutually exclusive events like getting 1, getting 5, getting odd number, getting even number. Exhaustive events means set of events must cover entire sample space. That means if you take any outcome, it must belong to at least one of the events. There can't be any outcome which does not belong to any of your events, your interested events. So then we say your events are exhaustive. So those are two different concepts, right? So therefore now we have four possibilities: mutually exclusive, but not exhaustive, right? This one, not mutually exclusive and not exhaustive. This one, both mutually exclusive and exhaustive. This one, exhaustive but not mutually exclusive because they are overlapping regions. So those are two different concepts. Two different concepts. Okay. තවත් සැකනම් හොඳම වැඩි තව Go to the chat GPT and ask. Okay. Go to the chat GPT. Anyway, we are going to finish this. Differentiate between exhaustive events and මෙයාට අඳින්න වෙලා යන අන්ත ටිකක් අමාරුයි explain කරන්න. හරි. දැන් කියේ මම ඕනනම් group එකකින් generate කරලා දෙන්නම් කියලා. They cannot occur at the same time. That means PA intersection B is 0. Like getting head and getting tail. Okay, those are mutually exclusive. An exhaustive set of events, exhaustive if at least one of them must occur when experiment is performed. Again, experiment එක perform කරාම මේ outcome එක ඔය මොකක් හරි event එකකට වැටෙන්න ඕන. එකකට හරි ගොඩකට හරි. Okay. So that means events together cover the entire sample space. මේ events ටික ඔක්කොම sample space එක cover වෙලා තියෙනවා. හිස් තියෙන්න බෑ. Okay. Like getting 1, getting 2, getting 3, getting 4, getting 5, getting 6 are events. Now those events are exhaustive. Of course, these events are mutually exclusive also. Maybe let me know if you like a diagram or when illustrate. මම කියලා අඳින්න නැතුව explain කරන්න බෑ. එයා කියයි ඕන්න මම ඕන්න ඇඳලා පෙන්නන්නම් කියලා. Okay. ඇඳලා පෙන්නන්නම් කියලා. මොකද ඔක අඳින්න නැතුව explain කරන එක හරි අමාරුයි. අඳින්න නම් යට වෙලා යනවා හොඳේ. යන්දම අඳින්න මම අඳපු එක තමයි ආ. මොකද අඳින්න ගන්නෑ. Right. So right. So why are we interested in exhaustive events? Because Bayes' theorem is related to that. Okay. Right. So these are a little bit of exercises for you to differentiate between exhaustive events and mutually exclusive events. Okay. So getting an odd number, getting an even number. Is it exhaustive? Yes or no? Say my experiment is throwing a dice. I have two events, two expectations in, right? Getting odd number, getting even number. Is it exhaustive? Obviously, yes, because every number is either odd number or even number. Second one, getting odd number, getting a prime number. Is it exhaustive?
No.
Why not? So then you must give me outcome which belongs neither to A nor B.
All the odd numbers are prime numbers.
No, that is not the answer. I am asking, give me a contradiction outcome which belong neither to event A nor B. Then only we say that it is not exhaustive, right? If you can give me such a number, I will accept your answer, because then it is not exhaustive, because there are outcomes which are not part of any of these events. Can anyone give me an outcome which does not belong to any of these two events? Then of course it is not exhaustive. Then those two events are not exhaustive. So these two events are not exhaustive because numbers like 4, 6, they are outside these events. So therefore these two events are not at all exhaustive. Right? Because if you take 4, if you take 6, right? So they don't belong to any of these. Right. What about the third one? Exhaustive or not? If not, why? If not, you need to tell why.
Exhaustive.
Is it exhaustive? It is not exhaustive. It is not exhaustive. Because if you take number 3 does not belong to A because its numbers bigger than 3. And number 3 doesn't belong to even B also because even B is smaller than 3. So then 3 is not in any of these two events. So therefore, these are not exhaustive. Okay. Right. Do this example. This is a BIT question. But you don't need a Bayes theorem to do this. Quickly do this. If A and B are two mutually exclusive and exhaustive events, and PA equal 2 times PB, then PB is equal to. Right? So A and B are two mutually exclusive and exhaustive. So that means your events are like this. A, B. It's mutually exclusive and exhaustive. It has covered the entire sample space. Right? So then probability of A is 2 times probability of B. So that means if you have n number of elements here, sorry, n number of elements here, there must be 2n number of elements here. No, right? Yeah. So then this is 2n divided by 3n. This is n divided by 3n. Yes. Yes. So this one's probability is 2 times this one's probability. Okay. Then what is the probability of B? What is the probability of B happening? So what is the probability of B happening? N divided by, because if you have n number of elements here, there must be 2n number of elements here. Right? So therefore it must be n divided by 3n, right? 1 divided by 3. So this one's probability is 1 divided by 3, then this one's probability is 2 divided by 3. So then 2 divided by 3 plus 1 divided by 3 is 3 divided by 3. Of course, sample space, it must be 1. Right? 1 divided by 3. So you can use whatever the logic, but make sure you use logic, not magic. Okay, don't use magic, right? Just use logic, common sense, logic. Well, because these are exhaustive, PA plus PB must be 1. So that is another thing you can use. Okay. Right. Now we'll look at the total probability law, and then we'll look at the Bayes theorem. So actually two rules are there. We are going to look at both. Total probability law, and this is the harder part. These are actually the understanding total probability law is not difficult, but the question can be difficult, fussy, and the formula itself is lengthy. Right? So if you feel like, okay, this is too lengthy, too much, okay, so just forget about it because still you can get 80% of the question. Okay. if you get 5 questions, maybe just one question is from total probability law base theorem, or sometimes none of the questions are on that. Okay, but if you can understand. Sometimes you will understand, but you can't remember the formula. Okay, that is fine. Sometimes you understand everything, but in the exam, the question is fuzzy. Sometimes some questions in your paper, even I can't do it. Sometimes I can do it. Sometimes I also got into wrong paths. Okay, just because I can't do it, it doesn't mean that you can't do it, right? You guys are from the next generation, right? If we are from I3, you are from I7 and blah, blah, blah. Just give 1 minute. Okay. So what is mean by total probability law? Suppose you have events A1 to AN, which are disjoint and mutually exclusive. So that means it must be disjoint, like there's no such possibility. And it is exhaustive, that means it has covered the entire sample space, something like this. You can see it has none of these events are overlapping, and these events have covered the entire sample space. So therefore, mutually exclusive and exhaustive. That is A1 to AN. A1, A2, A3, A4, say AN. Let B be any other event. So that is completely different event. It has nothing to do with this A1 to AN, right? It's sort of some other event in the same sample space. So therefore, you can just draw it like this. It can be something like this. It can be something like this, right? It can be something like this. We don't care. But we have drawn it so that it covers all the events as well. But it's not a must. Okay. But because we want to get the general case, we have drawn it so that it covers bit of each and every other A to N events. But there's a possibility that this is zero. Okay. Or it's not inside that. Right. So then total probability says, rule says probability of B happening. That is, what is the probability of B happening? Because there's a possibility of B not happening also, right? Somewhere here. So probability of B happening is sigma I equal 1 to n, that is from 1 to n from those events. Probability of B given AI into probability of AI. I goes from 1 to n. In other words, your probability of B happening is probability of B given A1 happen into P A1 happen plus probability of B given A2 happens into probability of A2 happen plus probability of B given A3 has happened into probability of A3 has happened, and so on. Right? So that means probability of A1 happens into probability of B given A1 has happened plus probability of A2 happens into probability of B given uh, A2 has happened, and blah blah. Actually, I should have swapped these two. Let me swap those two. එතකොට වැඩි ලේසි මතක හිටිනවා. Okay. Right now, it will be a little bit easier for you to remember it also. Right? Probability of A1 happen into probability of B given A1 happen, plus probability of A2 happen into probability of B given A2 happen, and probability of A3 happen into probability of B given A3 happens, and so on. You need to do it for all the other A2, A1 to AN events. Okay. So this is called the total probability law. So you can use that at any time. Okay. And let's take an example. Okay. So the hardest thing is sometimes you can't find out what kind of a scenario is this or putting it to a diagram. Okay. Right. There are two bags, one containing 3 green marbles and 2 red marbles, and the other containing 2 green marbles and 4 red marbles. Okay. That means you have two bags. If we randomly select one of the bags, first we select a bag and then randomly select one marble from that bag. What is the probability that we choose a green marble? Of course, this you can do without total probability law also. Actually, this is a very simple question. We can even do this without total probability law also. Right? So shall we try to do this without total probability law? Just use our other knowledge. Right. So there are two bags. Right. If we randomly select one bag, so first we need to select a bag, right? So let's call it bag 1, bag 2. I'm just using the common sense and other knowledge rather than using total probability law. Okay. So what is the probability of selecting the first bag? Half. What is the probability of selecting other bag? Half, because two bags are there. Then if it is first bag, it contains 3 green marbles and 3 green marbles and 2 red marbles. So what is the probability of selecting green? 3 out of 5. Red, 2 out of 5. Then what about the other one? The other contains 2 green marbles and 4 red marbles. 2 green marbles and 3 red marbles. Sorry, 2 green marbles and 4 red marbles. What is probability of getting green? 2 out of 6. What is probability of getting red? 4 out of 6. And the question is, if we randomly select one of the bags and then randomly select one marble, so therefore these are the 4 possibilities. Bag 1 green, bag 1 red, bag 2 green, bag 2 red. What is the probability that we choose a green marble? So green marble is, this possibility is green, this is green. So what is this possibility? Because these are independent, right? These are independent. So that is 3 divided by 5, half into 3 divided by 5. 3 divided by 10. What about this? Half into, because we need a green marble at the end, 2 divided by 6. That is 1 divided by 6. So therefore, what is the probability? 3 divided by 10 plus 1 divided by 6. I hope this is correct. I just use my common sense rather than total probability law. So if you take 30 as the common thing, 9 plus 5. 14 divided by 30. Let's double check the answer first, because I just use my common sense. I don't know. I told you that when we get into these kind of levels, sometimes it can be fuzzy. Maybe just we go by wrong paths. Oh, correct, right? 28 divided by 60 is 14 divided by 30, right? Right. So that is, I just use my common sense rather than anything else. Okay. And just use tree diagram, because problem can be solved in multiple ways. as long as you are doing the logical things. Now let's see whether we can use total probability law. That is, probability of B is probability of A1 into probability B given A1 plus probability of A2 into probability of B given A2. And you can see that there's a connection bit like that also, right? But මේක අර රුක්සටහන අතර පොඩි සම්බන්ධයක් තියෙනවා. Right. So now our question is, right, now we know that what is the probability of A1, because it must be either A1 or A2. Okay, A1 or A2. So probability of getting A1 is half. So this must be half. Probability of getting A2 or second bag is half. And it is mutually it is exhaustive because always you take either first bag or second bag. There's nothing else. Either you take this or you take that. Okay. So then B is choosing a green marble, because there can be a green marble in my A1 bag. There are green marbles in my A2 bag. Okay. So therefore now it's a total probability law question. What we need is probability of B, because this is green marble. This is bag 1 green, this is bag 1 not green. This is bag 2 green, this is bag 2 not green. So therefore what is PB? Probability of B is we can say probability of A1 into probability of A1 given B given A1. අනිත් පැත්ත ලියන lazy මේක හරි. Probability of A1 into probability of B given A1. මොකද ඉස්සෙල්ලා bag එක select කරනවා, ඊට පස්සේ ඉස්සෙල්ලා bag එක select කරනවා, ඊට පස්සේ ඒ bag එකේ මේ blue එක තියෙනවා. මම ඒකයි මේක දෙපැත්ත මාරු කරා නම් මට තව lazy කියලා. හරි අපි එහෙම ලියමුද? නැත්නම් මට ඕක හදන්න වෙන්නේ අමතක වෙනවා. හරි. ඇත්තටම මට පේන්නේ ටිකක් දරා ගියත් පස්සේ මේක මේ total probability මේ රුක් සටහනම තමයි කියලා. හරි. I think now it's much clear for you. Right. So therefore PB is PA1 into PB given A1 plus PA2 into PB given A2, because there is a total probability rule. And PA1 is half, because you have 2 bags, you need to take one of the bags. Then what is the probability of a blue in A1 bag? Because there are 3 out of 5. Because altogether 5, there are only 3 green. Then PA2 half, because it's another bag. And there are 2 green out of 6. And therefore the final answer is 28 divided by 60, or 14 divided by 30, or even 7 divided by 50. Is it clear? Is it clear? Now, it's always good to look at the same problem in 2 different ways. So now either you can use your conditional probability and tree diagram, or idea about total probability law. What is the probability of B happening? But remember, it can be applied only if these A1, A2 events are exhaustive and mutually exclusive, and B is a different type of image event in the same sample space. Okay. Right. So this is another question. This question also, if you want, you can use tree diagram, or you can use this kind of a total probability law approach. Right. I have 3 bags that each contain 100 marbles. 3 bags. Bag 1 has 75 red and 25 blue marbles. Bag 2 has 60 and 40. Bag 3 has 45 and 55. I choose one of the bags at random and then pick a marble from the chosen bag, also at random. What is the probability that the chosen marble is red? You can see that it's the same question, just we have added one more bag. One more bag. Okay. So therefore, again, if you want, you can use tree diagram, or you can use total probability rule. Right. This time, probability of your bag is 1/3. Right, 1/3. And probability of getting red is 75 out of 100, and blah blah blah. Okay. This time its question is all about marble in red. Yeah. 75 out of 100, 60 out of 100, and 45 out of 100. Okay. So again, maybe I should change this so that your formula is easier to remember, use. Final answer is 0.6. Okay. Or you can use tree type. Okay. Fine. So now we want to move on to our final theorem, Bayes theorem. Now there's a lot of similarity between Bayes theorem and total probability law, because pretty much the scenario is the same, but we are looking at a different solution. We try to solve a different problem. Again, you must have a set of events which are disjoint and exhaustive. So that is a prerequisite, just like for the total probability. Okay, so you must have a set of events which are exhaustive and uh, mutually exclusive. That means cover the entire sample space and no overlapping. And again, let B be an event in the same sample space. But earlier, the formula was to find what is the probability of B happening, and what is the probability of getting green. Now the question is, if you have got, if B has already happened, what is the probability of that particular A1 has happened, or A3 has happened, or A4 has happened, or in general, what is, if B has already happened, what is the probability of AI happen? Right? So it's a conditional probability. ඒ කියන්නේ දැන්ටම අපිට green එකක් හම්බෙලා තියෙන්නේ. හරි. මොකද්ද තියෙන probability එක මේක අපි අරගත්තේ තුන්වෙනි මල්ල වීම. දෙවෙනි මල්ල වීම. හරි. දැන්ටම green හම්බෙලා තියෙන්නේ. දැන්ටම red හම්බෙලා තියෙන්නේ. මොකද්ද මේක දෙවෙනි මල්ල අපි අරගත්තේ මල්ල දෙවෙනි එක වීම. So this is a very little bit more interesting thing. Okay. So this is the formula. Probability of AI given B. And B වෙලා නම් AI ගෙවීමේ සම්භාවිතාව. So that is PAI into PB given AI. Okay. දැන් මේක උඩට මාරුණා හරි. අහන්න AI given B. This is PAI into PB given AI divided by PAJ into PB given AJ where J goes from 1 to N. In other words, PAI given B is PA1, sorry, let's say 1, or it can be 1 or 2 or 3 or whatever. PA1 given B is PA1 into PB given A1 divided by PA1 into PB given A1, then PA2 into PB given A2, PA3 into PB given A3, and so on for each and every one until AN into PB given A. අර පෙන්නති මේ දෙන්නක උඩයට මාරු වෙනවා මෙතනදී. ඊළඟ මෙයා ලිව්වට පස්සේ අනිත් අයත් මේවට එකතු කරන්න ඕනේ. මේක A1 වෙන්න ඕනේ නැහැ. මේක A2 නම් මෙතන A2. හැබැයි මෙතන එන්න ඕනේ A1, A2, A3 ඔක්කොම. රටාව බැලුවට පස්සේ ඔක මතක තියාගන්න බැරිත් නැහැ. හරි. So that is called Bayes theorem. Okay, Bayes theorem. So you need to understand the scenario, and of course you need to understand the formula. And if you have only two, right, rather than you have so many A1, A2, A3, A4, of course, then it is A given B is PA into PB given A divided by PB. That is a special case. That is a special case. Okay. The special case එක නොද තියාගන්න එක හොඳයි. මොකද ගොඩක් අයට දෙන්නේ මේ වගේ දෙකක් තියෙන එකක් තමයි දෙන්නේ. So that is a special case. Okay. That means you don't have a lot of A1, A2, A3, just you have A1 and A2. Okay. Or you can say A2 is your A bar. Oh, okay. Or rather than A1 and A2, we just call it A and A bar, B and B bar. So then this is the same formula, right? When we have two events, we can call this other event as A bar. Okay. Right. So don't worry about this one. This is something I have added extra. If you are interested in doing research and so on, because these formulas are heavily used, right? Right. So let's do this question. මට මේ ඕන මට මේක අයින් කරන්න පුළුවන් අනවශ්‍යයි ගැන බලන්න එපා එච්චර හරි. Right. For the exams, this is nothing to do with the exams, okay? Right. So this is, I think this is one of the past paper question. If fires are rare, but smoke is fairly common, that means 10%. Probability of fire is 1%, but probability of seeing smoke is 10%. Because smoke can be due to so many other reasons, not only for fire, for other reasons also smoke can be there. So therefore the probability of seeing a smoke is 10%, but probability of fire happening is 1%. And 90% of the fires make smoke. And at the same time it says not every fire makes smoke, but 90% of the fire makes smoke. The question is, what is the probability of fire given there is smoke? If you can see smoke, what is the probability of having fire? So that's the interesting question, right? What is the probability of, now you can see smoke. What is the probability of there's a fire? Assuming that these probability values are correct, accurate. Right. So these are the type of questions you may get. Right. So what is the probability of fire? 1 out of 100. What is the probability of smoke? 10 out of 100. So therefore, what is the probability of smoke when there's a fire? 90 out of 100. Because it says 90% of the fire makes smoke. Right. So that means if there's a fire, what is the probability of smoke? 90%. Is it correct? Right? Or you can say Fs, right? Probability of F this, probability of S this. Now what we need is, given there is smoke, what is the probability of fire? That is probability of fire given smoke. And we can use the special case of Bayes theorem, right? Bayes theorem. That is PF into PS given F divided by PS. And PF is given, PS given F is given, and obviously PS is given. So you get 9%. Right? So therefore, what is the probability of fire if you see a smoke according to this scenario? There's 9% probability of fire. Whereas දුම දකිනකොට 109ක probability එකක් තියෙනවා එතන ගින්නක් තියෙනවා. So that we use calculated using Bayes theorem. Okay, Bayes theorem. Okay, so usually you don't get these kind of multiple scenarios, right? Usually what you get is this kind of simple scenario, right? If you get a question, but not always you are getting questions, okay? So therefore, the probability of fire given smoke is by using the Bayes theorem special case or simplified scenario, we get it as 9%. Right? So this is another question. And again, the important thing is you put it into a diagram and see whether those are exhaustive, mutually exclusive, right? An art competition has entries from 3 painters, Pam, Ka, and Pablo. Okay, 3 guys. A put in 15 paintings and 4% of her work have won the first prize. B put in 5 paintings and 6% of her work have won the first prize. C put in 10 paintings and 3% of her work have won the first prize. What is the chance that Pam will win the first prize? Okay. Now Pam is also putting paintings, right? She put 15 paintings. But while Pam put 15 paintings, other guys also put in 5 paintings and 10 paintings. Right? 4% of the time, when she put a painting, she won't win it. Now she has put up 15, but she is not alone. එයා විතරක් හිටියනම් මෙතන මොකද වෙන්නේ? එයා විතරක් හිටියනම්. ඒ එයාගේ paintings වලින් 104ක් පළවෙනි prize එක දිනනවා. එහෙනම් 104යි. හැබැයි දැන් එයා තනියෙන් නෙමෙයි. එයා තනියෙන් නෙමෙයි වුණාම අනිත් අයගේ ඒවා දිනන්නත් පුළුවන්. හරි. අනිත් අයගේ ඒවා දිනන්නත් පුළුවන්. Okay, so you can see these are very tricky questions. Okay, so that is A, B, and C are the 3 guys. And because we have only these 3 guys, it is exhaustive. And this is win not win. So this is win by Pam. This is loss for Pam. This is win for Pla. This is loss for Pla. This is win for Pablo. This is loss for Pablo. Now the question is, what is the chance that Pam will win the first prize? So if it is a win, what is the probability that it is by Pam? Pam is A. Something like this. Right? A win එක Pam ට යන්න දෙන chance එක කීයද? If it is a win, what is the probability of it is painting by A? A is Pam. So you can use Bayes theorem. That is PA into PW given A divided by PA into PW given A, PB into PW given B, PC into PW given C. මේ ටික ඔක්කොම දීලා තියෙනවා. PA කියන්නේ 15යි ඔක්කොම තියෙන paintings කීයද? 30ක්. 15 බෙදීම 30යි. මෙයා 5 බෙදීම 30යි. මෙයා 10 බෙදීම 30යි. Now then ඒගොල්ලන්ගේ winning chance එක 4%, 6%, 3%. 4%, 6%, 3%. So therefore, what is the probability of PAM winning the price? 50%. 50%. 50ක chance තියෙනවා මෙයා දිනන්න. 50ක chance එකක් තියෙනවා. ඒක බැලු බැලමට හිතන්න අමාරුයිනේ. මොකද මෙයාට 140යි. 104යි තියෙන chance එක තියෙන්නේ. මොකද මේගොල්ලෝ එක්කෙනෙක් දිනන්නත් එපා. අනිවාර්යයෙන් මේ තුන් දෙනා එක්කෙනෙක් දිනන්න ඕන. මොකද කම්පිටිෂන් නැතිවම දින කෙනෙක් ඉන්නවා. දැන් මෙයා වැඩියෙන් දාලා තියෙනවා නේ. වැඩියෙන් දාලා. Right. Right. So it's challenging questions, right? But don't worry that every question is like that. There are simple questions also plenty of. Okay. Right. So from next week, we are going to do past papers, including probability questions. Okay. So therefore, I'm not going to do any specific question today because anyway, from next week onwards, we are going to do past papers. Right. So we take a small break. After the break, now the syllabus is over for the maths. We want to possibly finish SQL part for the database also because security is a very small topic. Okay, so then that syllabus is also over. Right. So now it's 11:14. Let's start at 11:30, and we will continue with SQL and possibly finish it SQL part. Okay. Right. Summary queries. Right. Summary queries are queries that gives you, rather than individual records, summary of your details like average of a salary, the maximum marks, minimum marks, number of records in that satisfy that condition. So those are called summary queries. Okay, summary queries. Right. So what are the summary queries available? So these are the functions available for summarize your data. AVG, average, minimum, maximum, sum, summation, count, number of records, right? And these are related to numbers, numeric things, but count is in general for records. Okay, right. So therefore, with count you can use star, but for other fields, or you can use a field also, but make sure for other things you use the field name. And it must be a numeric field name as well. Okay, so here name is field name, okay, not the name field. Okay, right. So let's do some examples. Okay. Right, so we have been working with the S2225, where we have the employee table. So we'll use the employee table because it has. Let me add now one or two records now. Okay. Right, so let me add one more record. ID is 50. ID is 4. Vicom. 300,000. Let's say department 5. Okay, so it's at one more. Let's say 5. Raju. Seven. Right. So we have a little bit more data now. Right. Say I want to find out how many records are there in this table. So then I can write select count star, say from employee, or you can say count name or whatever. Okay. So the answer must be there are 5 records. It says 5. Okay. Right. So then we can use max, min. Right. So remember we have a numeric field called salary. I can use something like, say, sum, or let's say max salary from employee. That is, what is the maximum value of salary in the employee table? So the answer must be what? 300,000, right? 300,000. Yes, it is 300,000, right? So likewise, average, sum, those things are there. Okay. Right. So now there's a small thing here. Now, when you use the summary queries, if you want, you can group by a particular field. For example, now this is the, okay, let's say take the sum of the salaries. That is the total salary of all, in our case, all 5 employees, which will be somewhere around 1 million. Yeah, 935,000. That is the total sum of all the employees. But if you want, you can group by, right, say department ID. Group by, that is another keyword. Department ID. That means department wise, we sum the salary. We sum the salary. Right? What is the total salary of department 1 employees, 2 employees, and so on. So these are department, but it doesn't make much sense, right? So therefore, shall we have department ID also? The department ID, comma, sum of salary. So that means each department, what is the total salary? And it makes more sense. Right. Department 1, total salary is 130,000. Department 5, 42,425,000. Department 7, 380,000. That means only these department employees have salaries, right? Let's see whether do we have any employee other than 157? and see whether department 5 total is it correct? 425,000. Yes, we have only 157. Okay. For example, department 5 total salary must be 425,000. 300,000, 125,000. Department 5, it must be 425,000. Yes, correct, right? Right. So that is how you do it. Right. And remember, in the select statement, now you can't take something like, now remember, employee table has a field called, for example, name. But now if you try to take name here, it doesn't make sense, right? Because this is the total salary of department. So department ID makes sense because you group by department ID. But if you try to use something like name, it doesn't make sense, right? It may not give you error, but it gives you sort of a weird results because it doesn't make sense to include that here, right? So maybe you get the first employee of that department when you summarize it, okay? But anyway, this doesn't make any sense at all, okay? So therefore, don't do this kind of unsensible thing, nonsensible things. But just remember, it doesn't give you error also, right? So the other thing is, you can use this with where, right? Say, I want to calculate department-wise salaries, but if the salaries, individual salaries, bigger than say 100,000 only, sorry, 200,000 only, you need to take it. Otherwise, ignore it. That means I need to calculate salary of the employees whose salary is greater than 200,000. Then some those, that means only those some department wise, those who are getting salaries bigger than 200,000. So then obviously the results must be department 5, 300,000, department 7, 250,000, because these salaries will be ignored, right? So how to do that? So you can use the where condition. Select department ID, sum of salary from employee, where salary greater than 200,000, group by department ID. Still, you can use where condition. Where condition. Is it correct? 200,000? Oh, this is not 200,000, right? This is 20,000. That is why I got wrong answer. Right now, it should be okay. No, because I should not get this record, right? I should not get department 1. Right. Now I don't get department 1. So department 5, I got only 300. Department 7, I got only 250,000 because peak sum only those who are having salary bigger than 200,000. And we sum those. Okay. So that means while you use group by, or even while you use summary queries, you can use where condition. And not only that, while you use group by also, you can use where condition. Okay. Now you can write something like this also. Say sum of salary from employee where salary is greater than 200,000. So all the sum of all the employee salaries whose salary is greater than 200,000 only we consider. Okay. Here we take only salaries greater than 200,000, but not only that, you group by department ID. Okay, so that means while you use group by, still you can do the where. Now there's another part Okay, let me put it into next line so that it makes more sense. So that make it more sense. Okay. Right. So remember this where condition initially filter records before applying the summary function. If you want, after applying the summary function also, you can filter out. After. So that means something like this. So let's say initially no filtering. Right? That means you take the summary, sum of salaries of each employees, but department wise. Okay, let's execute this again. So we have department ID also. Right. So this is department wise salary, sum of the salary. Now let's say I want to see the sum only if the sum is bigger than 300,000. So that means the total sum is bigger than 300,000 only. I need it for a maybe report. So that means I don't want to see this first result because the total for that department is not 300,000. How to do that? Because that is after summation, you need to filter out. So that is where you have having another keyword. You can say having. In the having clause, you must use the summary function again. Sum of salary greater than 300,000. So that means take the sum of salaries department wise. If that sum is greater than 300,000 only, show it. Otherwise, skip it. Skip that sum. Now, when I execute this new query, this record will not be there. Right? Only the department 5 and 7 will be there. Because we have filtered out the final result. So if you want to filter out the final results, make sure you use having, not where. Right? Having is to filter out the final results. And to make things even more interesting, if you want, you can use both where and having together. That means where is used to filter out the initial results. Having is used to filter out the final results, summary results. Okay. So these are some interesting scenarios where examiners can give you challenging questions. So now what we do? So select department ID and sum of salary from employee where salary is greater than 200,000. We take the sum only for employees where salaries are greater than 200,000. And at the end, the final results are also filtered. If the final sum is not greater than 300, we again skip it. So there are two types of skipping. Some records are skipped, some results are skipped. Some records are skipped because we have where condition. Some results can be skipped because we have having condition. So two filtering. Initial filtering where, final filtering having. Okay. Right. So here we have not got any answer, any results because none of the employees. Now, when we have, for example, when you don't have this one, right? So we may get some records. Right? When you don't have this one, we may get some records. Right? But you can see none of these sums are bigger than 300,000. So that is why we did not get any results later. But if I make it having more than 275,000, so then we will get this, but not this. Okay, let's do like that. Say 275,000. Now 300,000 record will be there, right? But the other record is filtered. So now you can clearly see this is initial filtering. When you take the records, this is filtering your final results. Okay, so you must be really, really sure about what we are doing. Okay, right. So there is summary queries with group by and also having. Right, now we'll move on to joining tables. So this is the most interesting and the most important part and most challenging part as well. Right, joining two tables. Before doing the joining, let's see how to do the Cartesian product. It's very easy. Right, Cartesian product. This is something like the sets cross operation, right? So Cartesian product is not very useful operation, but it's good to know that there's that kind of operation and what is the result. Okay, say select, say all from employee, comma department. This is not a join. What we get is Cartesian product. That means each you take one employee record and join with all the departments. Then second employee record, join with all the departments. If you have 10 employees and 5 departments, you will get 10 into 5, 50 records. Of course, maybe the employee is related to department 3, but you will relate employee into department 1, 2, 3, 4, 5, because this is not join, this is Cartesian product. Okay. So in our case, we have, okay, let me delete some of the department because it's too much. I will delete 9. Also, I delete 8, okay? And because I don't need too much of departments. Maybe I will delete this one also, right? Just 3 departments, it's enough. Right, so now we have 3 departments and I think 5 employees, sorry, 3 employees. So you can see that when I delete some departments, it has deleted some employees because last time I enabled cascade delete. Right, now I have lost some uh, employees. So therefore, let me add at least one more employee. Okay. So I 1, 2, 4 is there. Let me add another employee called ID3. Say Mohammed. Say HR department. Right, now I have a bit of reports. Now I have 4 employees. Okay, let's say this guy has no department. Okay, null, because that I will be using in joining list. So now I have 4 employees, 3 departments. So if I do a Cartesian product, I must get 14 records. So this is a Cartesian product. Select all from employee, comma department. It's a Cartesian product. You can see I got 12 records. First employee is connected to all 3 departments. Second employee, all 3. Actually, I have given same name twice, right? Let me change the name. Yeah, so let me change this guy's name. Say Patum. Let's write it again. Okay. So you can see first employee connected to all three departments, second employee all three, next employee all three. Anyway, this is not very useful, but this is called Cartesian product. Okay, Cartesian product. But the more useful thing is joining. We discussed about joining in sigma 5 notation also, inner join, outer join, right? Joins. Right. So there are two types of joins. Inner join, outer join. Okay, inner join, outer join. So let's first look at inner join. Inner joins are the most widely used joins and easiest to understand. So inner join will join only related records. If a particular employee's department ID is 5, so you join it to the department ID 5 data. If an employee's department ID is 3, you connect it to the department ID 3 data. If an employee doesn't have a department ID or null, still, then that record will be ignored. Right? That record will be ignored because that employee doesn't have a department ID. So that is how inner join works. Okay. Right. So there are two ways you can write it. Right. Approach 1. Approach 1. And so that inner join can be written in two ways. Approach 1 is something like this. Select all from, say, employee, inner join, department. Then you need to say on. So this should be your foreign key. Foreign key to primary key. So employee department's foreign key will be department ID. Say employee dot department ID, department tables ID. In department table we call it ID, right? Let me double check. Yes, we call it ID. Right. So department tables ID. So this is how you write inner join. Inner join. So what kind of records, what records we are going to get? We are going to get 1 Tamara this and department 5 details. 2 Patum and then department 1 details. 3 Mohammed 350,000 and department 1 details. So this record will be not there because this record is ignored in the inner join because this employee doesn't have a department. Let's see. So we are going to get only 3 records. Just 3 records. Other employee is not there because that employee doesn't have a department. Okay. So that is one of the drawback of inner join because if there's no connection, that record is totally dropped. Even the employee details are also not there. Okay. Right. So there's another approach of writing the inner join. But this is better approach because it's very descriptive. But for simplicity, we often the second approach as well. So there, you just don't say inner join, you just say employee, comma, department, where employees department ID equal departments ID. So just to make it simple, because this is easier to type also. But this is same as the above code. It's an inner join. You must get the exact same output. Exact output. But this time you have seen the data twice because we use the where condition. Okay. So ID, name, salary. Again, that employee without the department ID is not there. Employee without the department ID is not there. But each employee with their department details are there. But the employee without the department ID is missing because this is an inner join. So those are the same queries and same queries. Okay. So here also we got 3 records. Here also we got 3 records. Same records. Okay. And it's up to you to decide which approach you like. Right. Some people like this because it's short, but others like more descriptive approach. Right. So that is what inner join. But there are situations, maybe even though a particular employee is not related to department, we need their details also. Maybe someone will say, I need a report of all the employee details together with their department details. So that means even though a particular employee is not assigned to a department, still I need that details also. That is where outer joins are really important. And remember, we discussed about the outer joins in relational algebra. So there are 3 types of outer joins. The first one is left outer join. Next one is right outer join. And final one is full outer join. So you must know all. Right, left outer join means you take all the records from the left table and related data from right table. Super easy. Now this time we are going to get, if we have employee without department, with null department ID, still that record will be there. So therefore left outer join is also super important one, because we heavily use, sometimes we use left outer join more than inner join. So here you need to say left join. Right, left join. Your left is this, right is this. So left join employee, left join with department on this. Now we are going to get all 4 employee records. Even though one of our employees doesn't have a department ID, still we are going to get the employee details of that employee. Okay, let's see. You can see Bicom. Bicom is not belonging to any department, but that record is still there. That was not the case in inner join. Right? So that is why we say it's a left outer join. We discussed this, right? Right. So then what about the right outer join? So remember, we only have department ID 115. Department ID 115 because there are some other departments, but there are no employees for that department. So therefore, we don't get any details about those departments in inner join or left outer join. But if you want to drive it from the right or the department side, so that all the departments are part of your resource, and of course, all the employees related to that department must also be there. But even though there's a department without employee, we need that record. also. So then you can go for right outer join. Okay, right outer join. So still, this is my left, this is my right. Left is the first one, right is the second one. But now I need to say right outer join or right join. Now it is driven from department side. So therefore, the department without employees will also be displayed. But for those records, the employee details will be all null. Now you can see we have the marketing department. Though marketing department is not connected to any employee, still we get it. But again, now we can see again that employee without department is missing. Because now this is not a left out join, this is right out join. Right. Now we have the department without employee, but not employee without department. So now marketing department is there, but you don't have a BCom. Now, if you want both, that means you need employees without department as well as department without employee details also, both. So that is called full outer join. So in MySQL, this is how you write full outer join. You need to union left outer join and right outer join. Okay. And there's no single statement. So this is my left out join. And then you need to say union your right outer join. So that will give you the employees without department, department without employees as well. Now you can see I have the Vicom, the employee without department, and also I have the marketing department, the department 6, though it doesn't have any employees. Right? So therefore it's a union of left outer join and right outer join. Okay. Right. So we discuss all these joins: left outer join, right outer join, full outer join. Right. So the final subtopic is subqueries or queries of queries. So that means in the where condition, if you want, you can write another query. Though we very rarely do it, but those are possible. Okay. Most of the time, you must try to get rid of subqueries because subqueries are not very readable. Most of the time, joins may work. And also remember, when you join, you can join not only 2 tables, you can even join 3 tables. Okay. The employees join to project, project is joined to the some other table which is related to project and so on. So then you have more and more join consist statements or more and more where statement if it is the inner join. Okay. Right. Subqueries, you can see we, in the where condition, we can write another select. That is how the subqueries are written, but very rarely we need to write subqueries. And most of the times, rather than writing subqueries, you can use joins. Okay. Right. So let's try to write a subquery. I'll start with very simple one. Select all from employee. Select all from employee. That will give you all the employee details. Okay. I will say select ID, comma name. of all the employees. Yeah. Select all the employees. Now, if I want, I can do something like this. Right, so let's take the salary also. Right. Now I want something like this. I want the records where a particular employee's salary is bigger than its average salary. Okay. Bigger than its average salary. That means if department's average salary is 200,000 and if your salary is 300,000, we need you. But if your salary is 150,000, your record must not be there. So we can use subqueries to do this kind of things. Right. So how do you write this? Where the salary is greater than select average salary so this is the salary of all the employees, right? Average salary from employee. So if your salary is bigger than the average salary of all the employees, I need your data. Otherwise, we don't need your data in the result. Okay. Right. So shall we first calculate what is the average salary of the employees? Let's see what is the average salary of each employee. Sorry, average salary of all the employees. Just right. Average salary is 350,000. 350,000. Now this query is if your salary is more than average salary, which is 350,000, we need that record. Otherwise, we don't need that. Okay. Right. So that means we are going to get this average salary 350,000. Can't be, right? That is the max salary. I think I took the max salary. Don't, yes, I took the max salary, right? Sorry. I need average salary. Right? I need average salary, not the max salary. ABG. Right. So average salary of an employee is 226,000. 226,000. Now, who are going to be about 226,000? That means only employee 3 and employee 4. Now let's see whether it's work. So salary is greater than average salary. So you must get only uh, Mohammed and Vikum now, if the query is correct. And we have written a subquery also. Because this part, select. I think we need bracket. Yeah, we need bracket. Right. So we are not supposed to get only two records now. This is a subquery. This is my main query. So inside your main query, you can write subqueries to get values. But make sure you do it in a very, only the last two records are there. Right? So it's very tricky, especially when you have subqueries. But in the exams, you get these kind of tricky questions. Right? I have given you some exercises also. Okay. Right. This is another interesting concept in SQL, exist and not exist. This is very tricky. Very tricky. When to use exist, very rarely we use because it's very fussy area. But there can be situation it can be really useful. Okay. So exist means if there are matching records. Okay, if there are matching records. Not exist means if there are no matching records, get this record. Okay. Right. So this is an example like that. Okay, let me copy this. So this use exist. Right. What does this do? Select all from employee where exists. Select all from department where employee dot department ID equal department dot. Okay, let's call it department dot ID because in our table it is ID. So what now you can see here we use exist and also we have summary subquery. So this means select all the employees who are connected to a department. That means if this is the inner join, if the inner join gives you that record, take those records. So, okay. So this is a very complicated way of writing this, but this basically says, I need the employee details if that employee belong to a department or if the inner join gives that record. Okay. And here we use exist. Okay. So it's a very tricky area. Now I should not get the last employee. Oh, why is that? Unexpected bracket. Yeah, we need only one bracket.
Closing brackets.
Yeah, one bracket. Right, you can see. So that employee not having the department is now missing because we use exist. And if you want that employee not having the department, you need to use not exist. Not exist. Now we are going to get that missing the record, but these records are now not going to be in the output. Now we got the VICO because we use not exist. So like, anyway, this is just one use of exist. There are so many ways you can use this keyword exist and not exist, okay? And it's very tricky as well. Right, that's it. So I have given you a few more exercises and of course now you can do past papers. Right, so now we have only one more topic for that because we have finished this part. One more topic, data security. Then that syllabus is also over. Right, so these four topics we can do in one day. Don't worry, we can do it in one day. And probably next week I will be adding one more. I will try my best to add one more 7 to 10 evening session. Okay. Maybe we can finish software engineering there, or maybe we can do another web topic. Okay. Right. We stop at this point, right? Thank you.